Okay.
Okay, good. So, Professor Adam, I'm just going to speak with the Portuguese people for a couple of minutes just to introduce you. And then afterwards, I'm going to be back to you in English, of course.
Of course.
Okay?
Thank you.
Ok, then. Bom, boa tarde, gente. A gente está em mais uma tarde, quer dizer, a nossa tarde cheia de coisas interessantes e bastante inovação. Então, eu espero que vocês fiquem ligadinhos aí. Meu nome é Michele e eu vou estar com vocês nesse próximo palestrante. Bom, tô super motivada por ele, porque pelo currículo ele parece uma pessoa maravilhosa. O nome dele é Adam Wojtek. Ele é chefe do Departamento de Química e Bioquímica da Universidade Mendel, em Brno, na República Tcheca. Ele trabalha com biologia celular e molecular no campo do envolvimento de metalotioneinas no prognóstico de câncer. E o currículo dele envolve uma série de projetos, parcerias, premiações. E hoje ele vai falar com a gente um pouquinho sobre o papel dessas melatoníneas, como elas podem influenciar na carcinogênese, na progressão do câncer e na resistência ao câncer. Eu vou dar uma versão um pouquinho mais ampliada em inglês, tá? Só para ele ficar por dentro do que eu tô falando. Então, muito bem. Okay, so let's go in English now. So good afternoon, everyone. Thank you all for being here. It's gonna be an exciting evening for sure. So my name is Michele, and yeah, I'm gonna lead this next section here. So I'm pleased to announce our next speaker is Dr. Adam Wojtek. I'm sorry if the pronunciation is wrong. I guess it's correct. He has a PhD in cellular and molecular biology, or he worked with modern methods and approaches in tumor diagnostics. Today, he is the head of the Department of Chemistry and Biochemistry at Mendel University in Brno, Czech Republic. His scientific information comprises many awards, including projects for cancer treatment, multidisciplinary research to increase applications potential of nanomaterials in agriculture practice. This is different for us. The experience just go on and on with the CV with many collaborators all over the world. So currently, Adam is working on the role of melatonin signaling and its implication to the prognostic of cancer. And today, Dr. Adam will dive with us and share his knowledge on melatonin's isoforms as a double agent, the roles in carcinogenesis, cancer progression, and chemoresistance. So with no further ado, Dr. Adam, you can take it away. Thank you.
Thank you very much for very kind and nice introducing me. The pronunciation is pretty nice. You don't have to be afraid of that. Because in my language, I'm pretty sure that it is absolutely unpronounceable. But believe me, my first name is quite unique, even in the Czech Republic as well as in the world. I hope you can see my screen, please.
Yes, I can.
Perfect, great. Thank you very much for inviting me to this very nice conference and very nice session. And in that COVID time, the online sessions are part of our lives, and we have to go through it. And I will do my best to entertain you during the whole my presentation. And I would love to tell you almost everything about methylphenidate you were always wanted to know about them. Let me briefly describe where I'm coming from. It was very nice said. I'm coming from the Czech Republic, from the heart of the Czech Republic, city of Brno. To be honest, Czech Republic with their 11 million of inhabitants is very, very tiny compared to Brazil. And our city of Brno has nearly 500,000 inhabitants. We have more than 100 employees at our department, which is shown here. A very nice and pretty much old building, I have to say. Quite a lot of labs. And regarding to the structure of our department, we have 4 research groups, and I would love to tell you a little bit about all of the groups, maybe as an idea to cooperate or collaborate together. I will start with the group which is called Molecular Biology and Nanomedicine. In that group, we have been developing various type of nano and microtransporters. And from those which are based on bio-based materials and biomimicking materials, we do really love these small or large or even larger proteins called ferritins and apoferritins. These proteins are marvelous because you can decompose them under various conditions, but they are stable under other conditions. We have right now more than 20 types of such transporters, which differ from the point of view of their diameter or their stability. You can put inside drugs, we know, and you can quite easily distribute these ferritins, or even focus these ferritin aims these ferritins at something you would love to aim. We have been working with cancer, and our presentation will be about the cancer, about the tumor disease, but we also target right now viral diseases and fatty acid liver diseases, and so on and so on. And these so-called little bastards are really very useful, and we have been working with them for a couple of years. The second group, and it was mentioned, we have also a project where we have been developing alternatives to antibiotics. That means nano and micromaterials, which could serve as an alternative to antibiotic, and we have been applying those in plant protection as well as in veterinary medicine. We partially avoiding the using in the human medicine because it's quite complicated to translate the research from the lab to the market, if I can call it. But from the point of view of agriculture, we're quite successful, and one of our products is we do very hope so, is going to be approached at the market as a new protector of plants against bacterial pathogens. We have been working with hundreds, nearly 1,000 of different types of the nanomaterials, where I would love to highlight one of that, and these are based on the graphene oxide, which where we have the most experience. The third group is aimed at bioanalysis and genetic engineering. In that group, which is divided into two quite big subgroups, regarding to bioanalysis, we have been working with standard, robust analytical methods, mass spec, HPLC, scapular electrophoresis, and many of those, including the newest one, like in vivo imaging. And we have been working as well with genetic engineering, and we have been using CRISPR-Cas9 and following technologies to modify the genome of the algae. In that group, these guys have been working with the algae for a couple of years, and right now we have been trying to modify the algae to be able to decompose organic pollutants. The final group is the most technical one. These guys are engineers, and they have been working on the robust instrument on one side, where is mentioned MALDI mass spec. But on the second side, you can hear this green schedule or scheme of our own instrument, which have been developed by us, and it is a small version of larger bioanalyzers, and we are going to market it next year with our commercial partner. These guys are very much focused on the development of such type of devices, really devices, not only lab playing or scientific curiosities, but really functional devices. Let me go back to the topic of our lecture. I do not think so that I have to tell you a lot about the tumor diseases, but here you can see some future perspective, if I may say, of the number of cases, newly diagnosed cases, and as well as deaths. It's quite stressful to see that numbers. But what is the most stressful thing about the treatment of the tumor diseases? It's not about diagnostic only, but also it is about the treatment of the cancer and about the effectiveness of the treatment of the cancer. And if you recalculate the ineffective protocols and ineffectively treated cancer, you'll find extremely enormous numbers, which makes losses from the point of view of misused drugs on one side, and unfortunately less among us at the second side. And we believe that methylphenidate could be a key how to increase and enhance the effectiveness of the current treatment strategies. Who they are? Who are they? Metallothioneins are low molecular mass cysteine-rich proteins which consist of two domains, beta and alpha. And personally, I have been working with these proteins for more than 20 years. I started at the high school to discover these small, very badly detected proteins in human bodies, but we really love them. These guys can have 4 isoforms, and some isoforms can have their sub-isoforms. These proteins were discovered in 60s of the previous century, and the main and the most known and function of these proteins is coping and maintaining of homeostasis with essential metal ions at one side, and detoxification of the toxic metals at the second side. That means that if any type of metal, toxic and essential one, can pass through the cell membrane, there is a metal transcription factor 1 bounded to the metal transcription inhibitor. When the metal ions passing through the cell membrane, these complexes decomposed, and metal transcription factor is free to start transcription and translation of the metallothionein. And metallothionein can then bind the free metal ions, you can see here, and then metal transcription inhibitor can bind to the metal transcription factor, and metallothionein transcription and translation is stopped. The complex of metallothioneins with the metals, there are some shadows, and we don't know exactly what is happening, but we believe that metallothionein complex with these metal ions, the toxic one, can be transported to the kidney. But what is happening with the metallothionein and essential metal ions? These guys are extremely important, and it seems that these guys can serve as a source of mainly zinc. And if we are talking about metallothionein 3, we have to mention copper as well. These guys can serve as a source for these two type of extremely essential metal ions for hundreds and hundreds of pathways inside a cell. That means zinc transporters, enzyme activation, as well as transcription factors, and as well as a storage. As a storage for a cell to have actively zinc ions for its disposal, and this place is for us to find other functions of the metallothioneins and to prove our main hypothesis, which is that we believe that metallothionein are playing the key role in malignant transformation through the two types of their behavior. The very first thing is their oligomerization, which could be connected in some non-discovered way with the isoform pattern. That means that not all isoforms and sub-isoforms of the metallothionein, as I mentioned before, can oligomerize. But the question is, what these oligomers? What is the role of these oligomers inside a cell? Can these oligomers pass in the cell membrane? Because, as I mentioned, metallothioneins are intracellular proteins, and some studies tell you that you can find a higher concentration of metallothioneins in blood of patients with tumor disease. Our main output of that type of hypothesis is that oligomers of metallothioneins can bind even one order of magnitude more metals than the single monomers, and can serve to a tumor to enhance growing of a tumor. By that metallothionein can serve as a source of zinc as well as copper ions for growing of a tumor. That means that we believe that metallothioneins can be drivers to promote the growing of a tumor. And at the second point of view, again, we are talking about the oligomers. We are again talking about the different isoform patterns. That means that not all isoforms can form the oligomers. And these guys can, in the pretty much same time, can bind almost all known cytostatics based on metals. And the dissociation constants which have been discovered are extremely high. That means that methyl can really bind these drugs very tightly and can protect the tumor against these type of treatment strategies. That means that methyl can serve as a chelator of metal-biased cytostatic to failure the treatment. And we believe that at the very same time, and this is the reason why we call our lecture as methyl as a double agent. We believe that methyl can act at the very same time as driver for growing a tumor and as a protector against current treatment strategy, mainly based on the metals. We have several research phases to prove it in our very big project, and these research phases consist of development of the new type of methods to detect metal findings, to distinguish their isoforms, and to prove the existence of the oligomers, to evidence biologically at the cell level the behavior which I mentioned a minute ago. That means driver and protector theory. And then the very final stage, we would love to test our hypothesis found at the cell level, and we would love to test it at the animal level as well, and to develop some alternative treatment strategy which will be based on the immediate silencing of the specific isoforms of the specific isoforms of methyl to increase the effectiveness of the current treatment strategies. What have we done so far? We have been studying the methyl for more than 20 years, and then we have been solving that project for nearly 3 years. The very first research phase is the development of the analytical method. The very first method I used this 20 years ago was differential pulse voltammetry Brdíčka reaction. It is quite unique and unusually used methods. Even in analytical chemistry, I'm not talking about molecular biology, just electrochemical methods of analysis. And we found that when we have been analyzing the blood coming from the patients having the tumor diseases, we found a very different voltamogram. That means like a fingerprinting of such type of diseases. You can see the breast cancer and melanoma, which are in the very much of interest for us in this in this project, and you can see quite interesting accuracy. But the most interesting thing is not the accuracy of that method, because it's quite unique and it's not so easy to translate it. But would love to, and right now we have been working to decompose these voltammograms and to find what is behind, which type of isoforms are behind of that behavior as the melanoma samples. We have been analyzing one isoform by one isoform. We have all of them in our labs. We use bacteria to produce them and purify them and analyze them, and you can see that there are differences in their behavior. And we believe that we will find the pattern, the isoform pattern. That means which isoforms play a key role in breast cancer as well as in the melanoma. We have been aiming at developing of the method of detection methyl inside a tumor, and we found out very interesting behavior. Primarily, we developed a method which is able to analyze spatial distribution of any metal you can imagine in tissue slices. It's right now it's quite common. In the time when we have been developing it, it was not so quite common, but you can find you can get these type of results quite easily. These are maps of spatial distribution of zinc. Right now we are talking about the zinc. And on these 4 slides, on these 2 slides, that means C, they are called C. This is the carbon. That means number of, not number, content of the slice itself, to recalculate your results. And on that 2 graphs below, these are called zinc. There you can find the zinc content inside the slices. And the red color means the highest concentration, and the blue, it means you can detect anything. Therefore, if you are talking about the so-called healthier tissue, you will find very tiny concentration of zinc. But if we are talking about the growing melanoma, you can find extremely high places with extremely high concentration of zinc. And these places are those, if you can imagine the melanoma and melanoma growing inside your body, that part is exactly at the very neighbor to the host tissue. And it was not so easy, but it was quite logical. Would we be able to detect the presence of metallothionein inside pretty much the same slice to find out if there is a connection between concentration of metallothionein, content of metallothionein, and zinc? Yes, we did it. We did it in our father study. Again, it's development of a method. We used melanoma coming from the pigs, which have hereditary melanoma. There you can see the pig. It's male in mini pig. It's breed in the Czech Republic only. It's quite unique. And we found and we confirmed that the content of metallothionein is in agreement with the content of zinc in growing melanoma, and we have been continuing in that type of research. So let me kindly focus all of us on the biological evidence. That means the biological type of results to proving the protector as well as driver theory. Very easy slide, but very much saying we use CRISPR-Cas9 technology to knock in and knock out some types of isoforms, and we are going one by one. Again, we are screening all of that, and you can see, and when we are talking in breast cancer cell, concretely MCF7 cell, and we knock in MT2A isoforms, which was very lucky that we did that experiment. We significantly increased the ability of the cells to defend themselves against cisplatin, which is quite interesting. We repeated that with knockout type, and we decrease this ability, and we increase susceptibility of these cells to the standard treatment with cisplatin. That means that really we can talk about the thing that MT2A isoform can induce the resistance of breast cancer cells against platinum-based cytostatics. Not only MT2A is in the center of our interest. I'm skipping quite a lot of work identifying the main roles of all isoforms. The second very interesting isoform is MP3 isoform. This is a very special one because this isoform can bind copper ions, which is quite unique even in the human body. And we tested our hypothesis surprisingly on neuroblastoma cells because we believe that MP3, and not we believe it, it was found that MP3 plays a key role in a brain to maintain homeostasis of copper ions. Again, we did some genetic modification. We identify hundreds and hundreds of proteins which are somewhat connected, somewhat changed by the knock-in and knockout of the metallothionein. And yes, we aim our attention at the proteins which are capable to inhibit apoptosis and are down-regulated due to MT3 upregulation. And we use deep proteomics and microscopy, and I'm going to show you some of our later or very, very fresh results. The very full thing is that we again changes in the neuroblastoma cells when we knock in the metallothionein. You can see the some atypical morphology which is not observed for the non-knock-in cells. And we again find the very much same behavior as in the case of breast cells and MT2A isoforms. That means that knocking in of metallothionein 3 increase the resistance of these type of the cells to cisplatin. We move further and use the chick choliantoic membrane assay as an easy to use animal model, because in the Czech Republic you do not have to have the ethical agreement to provide this experiment when you finish the experiment till 17th day. Therefore, we would love to have easier animal model to prove the behavior of the neuroblastoma cells and their ability when we knock in metallothionein 3 to produce a resistant tumor. Here you can see the schedule of way to induce a tumor inside a chicken embryo. Here you can see the figure of the chicken embryo, and the main output of our study is that we found that the number of the cells in liver, lung, and brain decreased significantly compared to the untreated control. This is when we are talking about the standard neuroblastoma cells. But when we use the neuroblastoma cells we knock in of metallothionein 3, which are resistant to the CDDPV, that means resistance to cisplatin. Here they are. Cisplatin did not exhibit any significant inhibitory effect on tumor weight or metastatic spread to the tested organs. That means that when we produce a tumor using the resistant neuroblastoma cells, we found that the tumor is resistant as well, and very much resistant. These you can see on that slide. These results are extremely significant. Let me move forward. Which is here now. Great, perfect. Yeah, and that's what I say. Cisplatin can inhibit the metastasis, but in knock-in cells, unfortunately not. I'm trying to move another slide. I'm sorry. Perfect. And this is the very much output that human MT3 upregulation neuroblastoma cells and its impact of susceptibility to cisplatin is extreme. It is enormous, and we are continuing in that type of research, and we have been trying to confirm our results by going to the animal model as well as going deeper inside the cell one. Here you can see another type of the cells you can have and before, and the pretty much same knocking in, and again upregulation of metallothionein 3 increased resistance at these cells as well. Sorry. Again, I'm perfect. We again repeat the experiment with the chicken embryos, and the results are pretty much the same. Another cell line, but the results are very much the same. Knocking in of metallothionein 3 induces the resistance of the tumors which are produced from such type of cells markedly. Now we have been working to deeply analyze our results from the cells and from the chicken embryos experiment. We are going further with the mice experiments, and we have been trying to identify the whole protein cascade which is behind of that very interesting behavior. At the very end of our pathway, we would love to prove that metallothionein 3 could be a key in treatment of neuroblastoma, because it's quite complicated to treat these tumors, and to confirm that the resistance of such type of tumors is connected to the metallothionein 3. Yeah. Let me go briefly to the conclusion, because we are going a little bit. We have limited time. At that very overwhelming slide is a conclusion of not only our research, but also the research coming from other labs which are aimed at methyl-thymine. And what we can say at some level of probability is that these things can say that it's p53 is downregulated or up regulated due to methyl-thymine, and you can see as well as here. And on this very, very big slide, I would love to tell you a little bit about the pathway, how methyl-thymine can induce the resistance of the tumor cells against anti-cancer drug. Here you can see the anti-cancer drug and the anti-cancer drug passing through the cell membrane, and the anti-cancer drug is free to be used or to be bound to something. Yes, very often it's producing reactive oxygen species and attack mitochondria in the very first stage. Methyl-thymine are going to be seen and are going to catch all of these ions, and this complex methyl-thymine cytostatic based on the metal complex is extremely stable. This complex probably go to the Golgi and most probably is excreted from the cells. And as I showed you a couple of minutes ago, these complexes can go to the kidney directly. The stimulation of transcription and translation of the methyl-thymine in the presence of zinc ions we discussed before, but the pretty much same principle can be applied as well as in the presence of other types of ions, including the platinum or palladium and rhodium. And on this part of our slide, you can see the connection of zinc methyl-thymine and methyl-thymine without metals with p53, matrix metalloproteinases, and as well as the proteins which are connected with angiogenesis, because I'm going to show you the second concluding slide. We believe that methyl-thymine, this is quite easier slide, methyl-thymine can activate proteinases to let cancer cells grow easily, more easily than it's possible due to the activation of such proteins, and as well as methyl-thymine can activate VEGF and to very much promote the angiogenesis. This is quite new, quite discussed, and we are going to have a look deeper as itself. At the very end of our lecture, I would love to mention that we believe that methyl-thymine can serve as a driver and as well as a protector at the very same time in a cancer cell, and making targeted therapy could make a tumor more vulnerable to current treatment strategy. Therefore, we are not developing a new type of treatment strategy. We have been trying to increase the effectiveness of the current ones. And at the very final stage of our ERC project, we believe that methyl-thymine could be called as a general tumor development mechanism for some type of tumor. That means a driver. As well as through the inactivation of methyl-thymine, we can enhance the effectiveness of current treatment strategies, which can unlock new possibilities in treatment strategies. I'm talking about switching off and switching on the expression of specific methyl-thymine isoforms. And this is one of our most valuable goals to show that not all methyl-thymine isoforms are the right ones, are the right targets for our studies and to be studied in a tumor and iteration with a tumor development. We believe that at the very final day of our research, we can shorter the treatment period, which makes obviously higher survival. ladies and dear gentlemen, thank you very much for listening to me, and I would be very happy to answer your questions. Thank you very much. And I don't know if I should end the screen, or I will make it like it. Thank you very much again.
Okay, thank you very much. Thank you very much. It was a very nice talk, outstanding lecture, very friendly. I was completely engaged on it, and I have some questions for you, but let's see if I have some questions here in the audience. It was very nice work, Professor.
Thank you. Thank you very much.
Yeah, we have a question from Stella.
Please.
She's asking which vector was used to knock in the MIT-L3 by CRISPR-Cas9.
Oh, brilliant question. And I will be extremely honest. I have no bloody idea. I can't remember. But if you don't mind, I will answer it. I'll answer it by the email. You will find it in the paper we published in Self, I guess. But I will send you that. I'm sorry. I don't know. Right now, I don't know which vector.
So I have a question.
Please.
Hi, Adam. So fantastic talk, really fantastic talk. So I'm at the beginning of the metallothionein, so I'm sorry if I ask you some naive questions. Forgive me. So did you try to classify melanomas or neuroblastomas, take into account the level of expression from different metallothionein isoforms?
You mean that
different behaviors, if there is high levels of some isoform, this is not a good outcome from the patient, something like that?
Yeah. It's a brilliant question. It's really not a stupid one. I didn't mention that, but there is a great difference between the expression of some isoforms and their translation. We still do not know what is behind, but you will find extremely high expression of some types of isoforms in melanoma as well as in neuroblastoma, and these are different. We are not talking about the same one. Therefore, we pick it up the MT2A and MT3 because it was based on some of our previous results that we got samples from a patient suffering by these two types of a tumor, and we screened the expression of various types of isoforms. But unfortunately, very often you will not find more than half of the highly expressed metallothionein. You will not find their protein form, and we still do not know why. What is happening when you have really high expression? When we are talking about MT1, MT1 is highly expressed in both, but you will not find. You will find some very tiny content of these type of isoforms in the sample. We really do not, or we really do not know what is behind. Therefore, yes, we screened both types of human samples, and from that, our research started.
So, you have one more questions from Maria Carolina. Do you want to ask Maria, or should I?
Sure. Hi, Adam. Thank you for the lecture. It was very good. I have a question concerning this personalized therapy. Could you administer that by injection, or should you administer that by orally, or like a patch or something? How do you suggest we could use the metalloproteins?
Maybe I don't know if I got the main idea of your question, but I will try. If you are talking about a drug, which could be how these could be administered to you, and the drugs can knock out metallothionein. If I'm wrong, please stop me. And yes. I will continue. Yeah. Our results, the best result we have is not oral administration. Unfortunately, it doesn't work because of stomach and these things. We believe in intravenous administration. We tested in another type of experiment some administration of our nano vehicles. That means the nanotransporters, which should be used as well as in this project, and we apply them intravenously, and the effectiveness was quite high because we use the ferritins, and these ferritins are not decomposed by our immune system because these ferritins are human ones, therefore human likes, and our immune system doesn't react to them. For there's almost no immune reactions, and these ferritins are modified very easily from their surface to go to the place where we would love to have them. That means a tumor surface at one side, and this whole process were tested on several application scenarios with different type of drugs, and the effectiveness of that approach seems to be extremely high. You don't have to use the antibodies on the surface of such type of transporters because it's quite the costs are quite high. You can use very easy organic compounds like folic acid and so on, and through that you will target the surface of a tumor very easily.
Thank you.
Good.
You're welcome.
Cesar, you can take it away.
Yeah. Great. With a very pleasure. Yes, we would love to. Of course. Our device, I didn't mention, but we have also developed a PCR on chip. This is the part of one of our group. It's quite popular paper published in Nature Medicine. Yes, with a very pleasure. Yeah. Please send me an email, or I will contact Monsieur with the answer on that question of the vectors.
Yes.
Shame on me that I didn't know it, and I will share this information. Please go through him or contact me directly at my email, and we can Skype, we can Zoom, and we can discuss it, and we can present you the device I mentioned in a very second. We have nearly developed that device. Yes, I would be very happy. Thank you for that. Okay. You are very welcome. You are very welcome. Marseille and France, it's not far away from Brno. Therefore, it's 2 hours flight, and you can touch us easily. Yeah, splendid. Thank you. Looking forward.
Yeah, for sure.
Yeah, I have my own question. So I like this road of collaboration, so hopefully gonna work very fine. But yeah, I have some questions coming back to the lecture. Actually, I was really intriguing with the fact that Metallo thing. Okay, again, because his name is really complicated, I have to really focus.
Don't be afraid.
Okay. So they can drive tumor growth, and also they can decrease it. And it reminds me a molecule called NMDA, that is a glutamate receptor that can go in the central nervous system. And I'm coming back to this topic because, as I said in another lecture, my background is neuroscience, so I'm always leading to this direction. But now I have a question in the cancer direction, that is, it's driving me to think what is going on behind this molecule. How can we manage when they have this drive tumor growth or the decreasing of the tumor growth? What's behind such a double-edged sword behavior? Like, what do you think that could be the reason why? Should be downstream signaling? Should be the isoforms itself? Should be cellular localization? Because I guess it's cytoplasmic, but I'm not sure if it could be find such a protein in the nucleus of the cell. So it got is intriguing to me that such a molecule can have two different behaviors, because I work with this in my doctorate, and it came out very nice story, because we have something that can be to the pathogenic route, another thing to be blocked or to be knocked down just to prevent the disease formation. So I guess it's really nice for science and to develop new tools to insert in the health field, let's say. So what do you think is the behind the mechanism?
Brilliant question. This is the reason, your question is the reason why methylphenidates are so destructive and not well accepted by the whole scientific community, because the results are completely against each other. What could be the behind isoform patterns? We believe that the isoforms are the answers. Therefore, we have to be sure that we can distinguish each isoform from the rest of the ones, and then we can really confirm that this methylphenidate isoforms can promote or can enhance the growth of a tumor. At that, methylphenidate isoforms can do the opposite. In one of our ongoing experiment, we found that knocking out of some isoforms do not induce anything, but knocking out the right one can induce even those which are not induced at all. Therefore, there is a pathway, and there is probably a protocol of inducing of several methylphenidate isoforms. Therefore, maybe the key will not be the knocking out of one or this methylphenidate isoforms. Maybe it will be the knocking out, of course, not for the whole time, but for some time, for the limited time, of 3 or 4 methylphenidate isoforms to make a tumor more vulnerable. But we believe that the isoforms are the answers on that contradictories about the methylphenidate research.
Okay. Yeah. Thank you. I guess it was the what I thought that could be. But you also mentioned about neuroblastoma, and it got also interested to me, because I'm not sure if these proteins can be colocalized with glia cells. Do we have some information on that, or if the proteins can be located at the nucleus of the cells, or just at the side?
I'm sorry. I forgot to answer on your question. The theory tells that methylphenidates are intracellular proteins, and that's it. But unfortunately, the life is more colorful than theory, and you can find methylphenidate outside the cell. We don't know how is it possible. The localization of methylphenidate inside the nuclei is possible, and you can find some papers where this has been performed, but it's quite rare. And localization of methylphenidate in the intracellular space, I mean, Golgi, mitochondria, it doesn't seem so. It seems that methylphenidates are more free, not to bind to anything. But This is extremely theory, and I'm highly, it's highly speculative. I should not have, I should not be right at all. But our inability to have really good antibodies against methylphenidate, and because methylphenidate has 5 to 10 kilodaltons, it's quite small protein. It's really not so easy to localize these proteins inside a cell. Even as I mentioned, we do not have a battery of antibodies to all of the isoforms. We are very lucky that we have monoclonal antibody against MP3. It's quite precious, and we are very happy to have it. We have really good antibody against MT2A. We have good antibody against MT1, and the rest one we have to use the polyclonal ones, and the results are not so good to tell you exactly where the methylphenidates are in the intracellular space. But the interesting thing is that they can pass through cell membranes to the extracellular space, and the reason why and their behavior and their effects there are quite unknown.
Okay, perfect. The good thing is that we have a lot of things to discover. So the science never stops.
Thank you.
Okay, I guess we don't have more questions.
No, I have one.
Okay. Go ahead. Sorry.
Oh, hi, Adam. I think everyone is excited about the empty molecules. Okay, I will call them empty molecules. That's okay. So, you show us the results from the empty tree. When you lock down the empty tree, you can increase the resistance to cisplatin, I think. And the results from lung, liver, and neuroblastoma was very similar to each other. What's really good, because it's so difficult to us to find some common path different, such kind different of tumors. So this is really cool. But I would like to know if you are capable to solve, if you consider different situations, and mainly in metabolic conditions of cancer, like hypoxia, starvation, oxidative stress, all these conditions are related to chemoresistance. So if you put this in the same tumor, the kind of isoform or the kind of level of expression of MET are different or no?
Marvelous question, I have to say. Hypoxia is one of our more target. We would love to. We would love to. We have been studying the relation between hypoxia in a tumor and methylphenidate expression and translation, and there are some association. That means that methylphenidate can also react on the presence of reactive oxygen species. There is a pathway where you can stimulate the transcription, activate this transcription of methylphenidate due to the presence of reactive oxygen species, and there is definitely an association. We do not know the exact pathway, but yeah. We are going to define it, and as a byproduct, I didn't show you that results, but as a byproduct, we found the role of MT2A isoforms, including non-fatty acid liver disease. That means that if you will knock in, or if you will change the expression of the MT2A, you will see extremely marvelous results when we are talking about that type of disease, which is mainly connected with the reactive oxygen species and all stuff around. Therefore, very, very good question, and there are some interesting associations. But it is not the lecture about the tumor. Mainly, it is this lecture about fatty acid liver disease, and I have to admit it, I'm not expert in that. This is one of our very, very close cooperation with the guys from Spain, and the results are marvelous. And I'm waiting to we have been waiting to publish it soon. I do very hope so.
Yeah. So I have just one more question. Sorry, because we have 3 minutes.
Yeah, yes, for 3 minutes. Sorry.
Yeah, so we have time. No, we have time. Just a little question. So if there are some of methionine isoforms that could be transported inside extracellular vesicles, because I'm starting to think about tumor heterogeneity, and maybe one cell could send the extracellular vesicle with methionine to the other, and that other becomes resistant also. So you know something about it?
Yeah. Oh, wow. But nice idea. We can
do this together. Okay.
We can study. I'm sorry. We have not done before that, but I think it's possible due to these vesicles. It could be possible. Thank you for the hint.
Okay. Probably tomorrow we'll send an email with like a brainstorm.
Please.
Wait.
Thank you very much.
Yeah, you're gonna receive one from me with more questions for sure. Obviously.
Okay.
I guess then we don't have more time. It was a very, very entertaining afternoon. Thank you very much, Professor. It was very nice for me, for everyone, for sure. Thank you for sharing with us your knowledge and your time, and hope to see you soon in Brazil and Czech Republic and whatever place you have.
Thank you very much for inviting me. I enjoyed a lot. Thank you, guys.
So thank you very much. Bye.
Thank you.
Bye.
So our next guest is Dr. Stephen Reed. I think he's online. Doctor.
Yeah, I'm here.
Hi, how are you?
Hi, Carolina. Thanks. I'm okay.
So Dr. Stephen Reed has lived in Brazil before, so he has asked us to give his presentation in Portuguese. So I'm going to switch to Portuguese now. Is that okay?
Okay. Vou tentar. Vou treinar com vocês. Vou treinar com vocês.
Que coisa boa.
Ótimo. Não, mas eu agradeço o convite. Eu gostaria de visitar. Infelizmente, nós temos que visitar nessa maneira agora, mas no futuro, quem sabe.
É verdade.
Hoje eu quero... hoje, ótimo.
No futuro, a gente vai tentar fazer um aqui no Brasil, né, Moacir?
Era grande prazer receber Beatriz aqui por um tempo. Era ótima pessoa. Infelizmente, quando eu vou lá, talvez ela não está mais. Mas
Vamos
ela vai
ver,
voltar, com certeza.
Com certeza, Carol. O próximo vai ser no Brasil. O Steve vai se juntar.
Beatriz já colocou aqui, let's see.
Gostaria muito.
Então, antes de eu passar a palavra, só fazer uma breve apresentação. Então, o Dr. Stephen Reed fundou o Instituto de Pesquisa em Doenças Infecciosas em Seattle, em 1993. E suas nomeações atuais incluem fundador e cientista distinto desse instituto, CEO da Onco Inc., professor adjunto de medicina na Universidade de Cornell, que fica em Nova York, e também professor pesquisador de patobiologia na Universidade de Washington. Em relação à sua formação, o Dr. Reed recebeu ele é doutor em microbiologia e imunologia da Universidade de Montana, em 1979, e naquele mesmo ano ele foi nomeado como cientista do Instituto Nacional de Pesquisa da Amazônia, em Manaus, no Brasil, onde ele dirigiu pesquisas sobre doenças tropicais. O Dr. Reed ingressou na Cornell University, no setor médico, e em 1980, como professor assistente de medicina, continuou a trabalhar no Brasil como gerente do programa Cornell Bahia em Medicina Internacional. Em 1990, ele ingressou no Instituto de Pesquisa Biomédica de Seattle em 1984 e ficou lá até 1993, quando ele fundou o Instituto de Pesquisa em Doenças Infecciosas. Não sei se era microfonia, mas eu vou falar assim. Ele já recebeu várias verbas de pesquisa, 130 milhões de doações em várias instituições, como a NIH, do BARDA, do DARPA e da Fundação Gates. E em 1994, ele cofundou a Alcoholista Corporation, que mais tarde foi vendida para a GSK, onde ele atuou como vice-presidente, executivo e diretor científico até sair em 2004. Ele também fundou a Therapeutic, uma empresa de adesivos transdérmicos, onde ele atuou como presidente de 2005 a 2008. E em 2008, o Dr. Reed juntou-se com o Rick Altman e o Ralph Steinman e fundou a Immune Design Corp, uma empresa de terapia contra o câncer, onde ele atuou como cofundador e CEO até 2011. Então, os interesses de pesquisa têm se concentrado na imunologia de infecções intracelulares, imunoterapêuticas, e no desenvolvimento de vacinas e diagnóstico para o câncer e doenças infecciosas. E em parceria com a GSK, ele, inclusive, liderou a equipe que desenvolveu a primeira vacina contra a tuberculose definida para avançar nos ensaios clínicos. Ele desenvolveu também a primeira vacina definida contra a leishmaniose, bem como os testes diagnósticos baseados no K39, e atualmente é licenciado para o diagnóstico de leishmaniose em vários países. E tem mais de 380 publicações, 35 capítulos de livros e resenhas, 105 patentes emitidas na área de diagnóstico, vacinas e terapêuticas de doenças infecciosas e câncer. Então, Dr. William, é um prazer ter você aqui conosco e eu passo a palavra para projetar a sua apresentação.
Muito obrigado. Olha, quando eu cheguei em Manaus, eu falei um pouco de espanhol, mas nada de português. Quem me ensinou era uma técnica japonês, de Japão mesmo, e outra pessoa de Belém, sem dente. Ele falava assim. Então, eu um pouco enrolado, mas eu vou tentar apresentar em português hoje. HT, nova companhia que nós fizemos sobre tecnologias, principalmente RNA. Hoje eu vou falar sobre RNA, mas HT, nós temos um site, você pode visitar. Tem várias outras tecnologias contra câncer. Eu criei essa companhia 2 anos atrás para realmente achar soluções práticas para tratamento de câncer e doenças infecciosas. A HT dedicado tem tecnologias que poderiam ser usadas no mundo inteiro. E você não vai custar fortuna para se aplicar. Próximo, por favor. Hoje eu vou falar sobre RNA. E RNA é uma tecnologia que eu estava estudando por mais ou menos 5 anos, principalmente porque nós fizemos avanços em formulação. Depois eu vou conversar um pouquinho sobre isso. Mas nossos objetivos é oncologia, medicina, precision medicine, soluções individuais e para realmente vacinas contra doenças virais. Mas também eu vou falar hoje 2 coisas. Nem só vacinas, mas o potencial para RNA ser usado para terapia. Nesse caso, pode ser oncologia, poderia ser hepatite, poderia ser Covid. Mas tudo isso depende de formulação. Próximo, por favor. E esse é o esquemático do tecnologia que nós temos, que também outras companhias têm, principalmente a BioNTech. BioNTech, vocês talvez vejam notícias nos jornais ontem sobre resultados de Pfizer. Pfizer licenciou a tecnologia de BioNTech na Alemanha, e eles usam RNA, 2 tipos de RNA, mensageiro e replicon. Por esse estudo que eles acabaram de fazer nos Estados Unidos, era realmente mensageiro, primeira geração. Mas nós estamos usando o replicon, RepRNA. Esse aqui é o esquemático do sistema. Você tem vários genes que criar a replicon, e você pode colocar qualquer antígeno de interesse no fim para criar uma vacina muito rápido. Por exemplo, vamos ver, em janeiro, a sequência de SARS-CoV-2 foi publicado em China. E dentro de 5 dias, nós tivemos uma vacina replicon feito no laboratório. Dentro de 9 dias, nós estávamos já injetando animais. Então, isso poderia ser muito rápido. Agora, nós estamos atrás nesse processo porque a tecnologia é tão nova que FDA não permite a gente entrar em estudo humano imediatamente. Nós tivemos fazer vários estudos animais primeiro, mas tudo bem. Agora nós estamos preparando para a fase clínica. Bom, nesse slide eu estou mostrando vários tipos de tecnologias, evolução, vamos dizer, de tecnologia. Começando com vacinas viral, por exemplo, adenovírus ou pox vírus. Eles são interessantes, eles funcionam bem, mas como você sabe, com adenovírus, por exemplo, você pode imunizar a pessoa e eles respondem bem de vacina, mas também respondem de adenovírus. Então, eles criam uma resposta contra a vacina mesmo. Então, você não quer usar um vetor que é imunogênico, porque assim você pode neutralizar a vacina contra a próxima vez que você aplica. Essa evolui para naked RNA, ou RNA sem formulação. É interessante, mas a RNA é muito frágil, não é estável. RNA é suscetível de RNAs, você sabe. Então, essa tecnologia nunca foi desenvolvida porque pessoas não conseguiram usar com eficiência. Agora, 2020, século 21, nós estamos usando RNA formulado com nanotecnologia. E esse aqui eu vou dizer. Por que nós estamos usando nanotecnologia? Porque protege RNA e composição de formulação também tem moléculas adjuvantes e também quando você combina essas coisas de proteção e usa adjuvante também, você pode usar dose muito, muito pequena. Nós estamos usando dose de humano 1 micrograma de RNA. E realmente, em camundongos, conseguimos usar 0,01 micrograma, é quase impossível nem imaginar, mas é verdade. E depois eu vou explicar por que isso é possível. Próximo, por favor. Vamos voltar para no início. Quando você já sabe de vacinas de RNA, quantos anos? Talvez 30, mais que 30 agora. Mas eles nunca deu certo, porque você tem que usar grande quantidade. No início, todo mundo achava que DNA seria muito simples, muito mais fácil fazer do que proteína. E é verdade, você não precisa usar cultura de células da mesma maneira, você não precisa usar ovos, por exemplo, se fosse influenza. Mas DNA, a dose é muito alta. E ele tem que entrar no núcleo para ser efetivo. Então, ele nunca avançou para ser produto eficiente. Depois, RNA. Como eu já falei, RNA era uma tecnologia com grande promessa, mas nunca deu certo por falta de formulação. Mas quando você pode, mas se você consegue injetar RNA, ele faz a proteína em vivo. Pensa bem nisso, muito importante. Seu próprio corpo está fazendo a vacina, nesse caso. Qual é a vantagem disso? A vantagem disso, você pode fazer rápido, como eu já falei, RNA pode ser produzido muito rápido, mas outra vantagem, a proteína está feita na forma natural, não é como o E. coli, por exemplo. E você não precisa purificar a proteína, tudo isso, e não vai acabar ser proteína que não é natural. Mas quando a sua própria célula faz a proteína, seu corpo está fazendo a vacina. Como se fosse um vírus replicando você e você monta a resposta imune contra esse vírus. Ok, então, próximo, por favor. Mas, replicando RNA é muito melhor ainda do que RNA mensageiro. Por quê? Porque, olha, replicando RNA aqui, quando você injeta uma molécula de RNA, é capaz sendo feito muitas moléculas de proteína. Muitos. Ninguém sabe exatamente quantos, depende de sequência de você coloca no replicon, mas pelo menos 10 a 50 vezes mais proteína está feita do que a quantidade de RNA. Quer dizer, se você injeta 1 micrograma de RNA replicon, você pode ter 10 a 50 microgramas de proteína. Dose razoável para a vacina. Mas produção, muito barato e muito rápido, e você quer vacina para a população do Brasil inteiro, você pode fazer numa fábrica pequena, porque você usa uma dose muito baixa. Do outro lado, mensageiro, RNA mensageiro, uma molécula de RNA faz uma molécula de proteína. Então, é relativamente ineficiente, você tem que usar muito mais RNA para conseguir uma resposta imune. Próximo, por favor. Esse é somente mostrando mecanismos. Pode ir para o próximo, por favor. Yeah. Mas, RNA necessita formulação. Como eu já falei, proteção. Olha, primeiro, realmente esse slide, o primeiro que foi inventado é Lipid Nanoparticle, LNP. Essa formulação que está sendo usada para Pfizer e Moderna hoje. Os dois companhias mais avançadas em COVID vacinas agora, hoje, são Moderna e Pfizer-BioNTech. Todos dois usam LNP. LNP é ótimo, ele protege RNA, mas olha, você tem que colocar RNA dentro de nanoparticle. Então, o processo de formulação é complicado e caro. Tudo bem, se você está fazendo vacina para os Estados Unidos, para a Europa, tudo. Se você quer fazer para o mundial, a dificuldade de fazer 5 bilhões de doses é insumável, não pode ser feito. Então, mais ou menos 10 anos atrás, parece um brasileiro, Brito et al., 2014, CNE, não aquele referência aqui. CNE era desenvolvido para a companhia Novartis. Esse é interessantíssimo, porque você tem caraaneclípidos e a RNA pode absorver da superfície de nanopartícula. Então, qual é a vantagem? Formulação muito simples. Apenas misturar RNA, aqueles cobre vermes, você está vendo? Misturar a RNA com nanopartículas. Tudo bem, ótimo. Então, Novartis ainda tem essa tecnologia, também pelo acquisition de Novartis, eles também têm. Mas, nosso grupo queria inventar uma coisa que não seria igual, por causa de patente, e também que poderia ser melhor ainda. Então, nós envolvemos lipid carriers, NLC, que dentro de partícula tem óleo. E isso é muito interessante, muito importante. O que o óleo faz? Ele estabiliza a partícula e também ele funciona como adjuvante. Ok? Por quê? Porque esse óleo é squalene, o que está usado em muitas vacinas hoje. Próximo, por favor. Ok, vamos ver dados. Qual é a vantagem dessa combinação de RNA replicon junto com formulação? Eu estou chamando isso versão 3 de RNA. Versão 1 era RNA só, versão 2 era RNA com LNP, essa aqui versão 3. Vou mostrar como. Próximo, por favor. Nós começamos com Zika. Porque na época, quando nós inventamos isso, a Zika era um grande problema, ninguém tinha proteína. Proteína demora para fazer. Se vocês fazem no laboratório, vocês sabem, não é simples, não. Qualquer proteína recombinante demora para fazer e demora para produzir grande quantidade. Caro e devagar. Então, nós começamos com RNA rápido. E você pode dizer, pode olhar aqui a vantagem de replicon RNA. Dá para ver a flecha aqui? Replicon RNA dá 100% proteção, a mesma quantidade de RNA mensageiro, 25%. Isso como damos. Injeção. Essa é outra coisa para lembrar. mRNA funciona bem, como resultados de Pfizer que anunciado ontem, mas você tem que fazer 2 injeções. Replicon RNA, porque a proteína está sendo feito durante um período, você só precisa de uma injeção. Lembra isso? RNA, como fosse uma proteína, você tem que injetar 2 vezes. Não está replicando dentro do corpo, mas replicon RNA, eles continuam a produzir proteína, basta uma imunização. Nós também estudamos carga viral, aqui no outro, com várias formulações. CNA, aquele que eu mostrei do Novartis, funciona bem, porque carga viral muito baixa, com 1 micrograma de RNA, e nós NLC igual. Então, isso funciona igual, tudo bem. Mas você pode ver, quando o RNA está injetado, mesmo replicon RNA, que é muito potente, sem formulação, não funcionou. Ok? Não está protegido e não tem aquele vantagem de formulação. Entendeu? A outra coisa interessante, RNA mensageiro, aqui, mesmo naked RNA, sem formulação, nada. Muito vírus. Mesmo formulado com LC, muito vírus. Não funcionou. Por quê? Porque com um dose, RNA mensageiro não funciona. Precisa de 2 doses, como eu falei. Ele não está continuamente fazendo proteína. Ok? Next, please. Ok. Vamos fazer essa tecnologia no Brasil. O que nós precisamos? Precisamos fazer RNA e nova tecnologia que a gente chama Leone. Essa nova tecnologia é a segunda geração do NLC. Lion, em vez de usar o óleo dentro da partícula, usa ferro. Ferro é uma molécula inorgânica e ele aumenta a estabilidade do nanopartícula. Muito importante que se você quer fazer a vacina em grande escala e se você vai distribuir para o país inteiro, na Amazonas, Porto Alegre, tudo, você precisa de uma formulação que é muito estável, que dura muito tempo. E como você sabe, ferro é muito duro, então ele ajuda a estabilidade de formulação. Não era só por isso que a gente escolhemos ferro. Escolhemos ferro porque já foi usado em várias formulações para imagem de tumores. Então, nós tomamos essa tecnologia porque já era aceito e modificamos para ser usada para RNA. Então, nossa vacina contra COVID é RNA replicon e formulação chama Lion. Próximo, por favor. Nós comparamos várias formulações no laboratório e aqui você pode ver teoreticamente, pelo menos, a vantagem de nossa COVID vacina em comparação dos outros. A vacina contra COVID, nós estamos chamando HDT 301. HDT 301, seguro, sim. Self-amplifying, ele replica em vivo, sim. Shot, sim. Estável, sim. Macacos, melhor dados no mundo nós temos. Shot protege macacos, outros só 1 ou 2 publicamos alguma coisa em macacos, principalmente anticorpos. Mas esse aqui é grande escala, scalable, é coisa que eu me anima mais. Eu sou muito excited sobre isso, porque eu quero fazer uma solução para o mundo, não só para Estados Unidos e Europa. E outra coisa interessante, nós temos a única vacina que usa o vírus que está circulando. Quando SARS-CoV-2 era publicado na China, era wild type, ok? A sequência era wild type. Mas, com o tempo, pessoas acharam que pessoas com COVID tivemos uma mutação. Então, nós rapidamente fizemos outra vacina com essa mutação. Então, HDT 301, única que tem essa mutação representa e cepa que está circulando agora na natura. Próximo, por favor. Como Lion ou formulação protege? Como eles funcionam? Eu já falei 2 coisas. Uma, ele funciona estabilidade. Ele protege contra RNAs. Sua produção tem que ser RNAs free para produzir RNA, sim, claro. Mas depois, quando você quer misturar e usar na clínica, ou guardar na geladeira, ou mandar para outros lugares, você precisa de uma formulação que realmente protege. Essa protege melhor do que qualquer formulação que existe hoje. Esse só funciona que você pode fazer uma ensaio muito simples, usando RNAs, mostrando que mesmo com RNAs, quando adiciona LION ou NLC, você pode proteger RNA razoavelmente. E também, outra ponte, estabilidade. Mesma relação de estabilidade de RNAs, proteção, quando você protege contra RNAs, você tem maior estabilidade. E nós temos estabilidade, melhor estabilidade é 25 ou 4 graus. Com 42, você começa a perder a potência. Essa figura mostra o tamanho de partículas. Nós queremos 50, mais ou menos 50 nanômetros, mas com o tempo, quando você esquenta com 42 graus, a partícula cresce um pouco. Não, ele continua funcionando, mas ninguém vai querer 42 graus. O ponto principal aqui, um mês, você pode conseguir estabilidade, pelo menos um mês, até hoje, estabilidade com 4 graus. Significante muito grande. Por exemplo, aqui nos Estados Unidos, eles estão preocupados agora quantos menos 80 geladeiras, freezers, eles têm que comprar para distribuir a vacina de Pfizer. Não é simples, né? Porque você não pode gelar e guardar a 4 graus. Mas aqui podemos misturar, podemos fazer e guardar menos 20, mas quando você vai querer usar, você pode misturar a LION com RNA e guardar 4 graus. Realmente, 25 graus não faz mal, mas 4 melhor. Próximo, por favor. Como o LION funciona, ele permite RNA entrar de célula, porque protege e a partícula de tamanho que a célula quer comer. 50 nanômetros até 100 nanômetros é ótimo para a célula ingestir. Então, ele facilita a RNA entre a célula para o citoplasma. Eu já falei sobre a vantagem de RNA sobre DNA. DNA tem que entrar em núcleos, mas RNA não. RNA só do citoplasma, onde ele pode replicar, produzir proteína, claro. Outra vantagem, Leon, que não está bem explicado aqui, é RNA contém adjuvante, squalene. Então, ele ajuda a resposta imune quando a proteína está feita. Então, essas duas coisas que a LION faz. Entrar e potenciar. Próximo, por favor. Quando você compara LION com outras partículas, LION funciona muito melhor em animais. Tudo bem, porque é por causa de increased potencial e propriedade de adjuvante. Essa figura nós estamos usando o reporter CEP, alkaline phosphatase, e medindo a quantidade de proteína feita, comparando o LION com a primeira geração NLC. E LION é bem melhor, quase 100 vezes melhor que NLC, pelo menos 10 vezes melhor. Então, ele faz mais proteína porque protege RNA melhor. Próximo, por favor. E, além de proteger a RNA para fazer proteína, ele induz a resposta imune maior por causa de combinação de adjuvante e proteção. E nós estamos olhando aqui contra spike, COVID. Você pode ver, não está descrito aqui qual é o candidato, mas tem várias formulações que nós estávamos tentando, e essa maneira como a gente escolhe a melhor formulação. Você vai escolher baseado no resposta imune e também estabilidade. Próximo, por favor. E camundongos são interessantes para começar. Pessoas acham que camundongos mentem, mas eu acho que realmente eles são muito importantes para as pesquisas. Eu sempre vejo na tuberculose, leishmaniasis, outras coisas que respostas imune em camundongos e proteção em camundongos informa muito bem o tipo de proteção que você vê em macacos e humanos. Mas, mesmo assim, nós fizemos macacos também. Lembra que eu falei, uma injeção só, conseguimos proteção. Você pode notar uma coisa muito interessante. Em um grupo, 1 dose só, segundo 1, 2 e boost, no dia 28, e terceiro grupo, uma injeção só. Mais ou menos tudo igual. Mas, no início, a gente não sabemos o potencial do RNA. Então, usamos uma dose estupidamente alta, 250 microgramas. Imagina quanta proteína está sendo feita quando você injecta 250 microgramas e cada molécula de RNA faz 10 moléculas de proteína. Muito só não morreu, mas ele aguentou bem, não era nada bom, mas interessante para notar que 25 microgramas igual 250. Então, esse tipo de estudo, informamos dose clínico. Nós vamos começar estudo clínico com 1 micrograma, e depois 5, e depois 25. Por que 25? Porque foi usado em pessoas idosas, por exemplo, ou quem é resposta imune que é comprometido por alguns problemas. Mas a gente acha que o dose humano seria 1 a 5 microgramas. De novo, isso significa que podemos produzir grande quantidade. Nossa ideia, em nossa colaboração com o Brasil e Índia, produzir mais ou menos, no início, 1 bilhão de doses e depois, até o ano que vem, 5 bilhões de doses. Próximo, por favor. Essa é só mostrar a histologia de macacos protegidos bem. Essa aqui realmente, o pulmão está cheio de inflamação, você pode ver. Próximo, esse controle, né? E aqui, pulmão mais saudável, pulmão normal, quando você olhava macacos vacinados. Mas o macaco não pega doente como igual ao humano, mas eles pegam patologia, então usavam essa maneira para medir eficácia. Próximo, por favor. Ok. Nós estamos agora preparando todos os documentos para a FDA, para a Anvisa e para a DBT na Índia, para poder começar o teste clínico em dezembro desse ano. Nós recebemos grande contrato por NIH. Esse contrato permite estudos no Brasil, Estados Unidos e Índia para produzir e testar a vacina em humanos. Próximo. Ok, oncologia. Isso porque eu criei essa companhia. Não era para a COVID, porque a COVID não existia na época, mas eu sempre tinha essa visão, usar RNA para responder rapidamente para vírus novos. Nós estamos falando com Fiocruz, por exemplo, no Rio, 2 anos atrás, sobre a febre amarela, Zika, chikungunya, usando essa plataforma. Então, isso vai ser feito. Mas também nós queremos usar para oncologia. Esse é um exemplo publicado há alguns anos atrás. Essa mulher, ela estava morrendo de câncer de mama, mas com o tratamento de neoantígenos dela, peptídeo, só peptídeo, junto com adjuvante, ela melhorou e continuando bem. Bom, neoantígenos, interessante, todo mundo sabe, mas eles têm limite, na maneira que eles estão usados até hoje. Qual é o limite? Pessoas dependem de peptídeo, e todo mundo sabe que peptídeos são fracos com antígeno, eles não são ótimos antígenos, e para funcionar eles têm que ser usados com adjuvante, e números de adjuvantes bons são limitados, né? Principalmente em mão de companhias, ou ainda no estágio pré-clínico. Então, essa tecnologia, mesmo que você identifique identificar o melhor neoantígeno, estimular a resposta contra os neoantígenos. Qual é a solução? RNA. Porque com RNA você pode expressar proteínas inteiras, proteínas que não poderiam ser feitas com tecnologias recombinantes. Eles usam peptídeos por causa disso, porque esses antígenos de tumores são muito difíceis de produzir, ou impossível de produzir. RNA, todos produzem, todos. Próximo, por favor. Então, essa é a nossa ideia. Você entra na clínica. Dentro de alguns dias, todo mundo agora tem a capacidade de fazer sequências de tumorais. Com essas informações, você pode identificar antígenos de tumores que são, por exemplo, próstata ou melanomas. Tem vários antígenos que a gente sabe que são conservados nos tumores. Ou você pode também identificar neoantígenos, que são únicos para aquele tumor. Com as informações, que leva 2, 3 dias, você pode mandar informação para o laboratório central, talvez sua universidade lá, e eles podem produzir RNA on demand. Ok? Esse RNA poderia ser feito em alguns dias, não algumas semanas, não alguns meses, alguns dias. Esse RNA poderia ser mandado para o hospital, e o hospital já tem formulação online, eles apenas misturar e começam a vacinar a pessoa. Assim, a tecnologia é barata e disponível para todo mundo. Não sei uma semana, mas teoreticamente sim. Uma semana, quando tudo está funcionando bem. Mas depende de quanto tempo leva para identificar neoantígenos. Mas, vamos dizer, dentro de algumas semanas, pelo menos, você pode ter um produto terapêutico para todo mundo. Ok. Qual é a promessa dessa tecnologia? Ou neoantígenos em geral? Você sabe que a imunoterapia, pessoas são animadas porque com checkpoint inhibitors, com CTLA4, por exemplo, você tem a eficácia em várias pessoas que não respondem a outras terapias. Por que checkpoint inhibitors funcionam? Porque eles deixam seu resposta imune natural funcionar. Eles são caros e a eficácia mais ou menos 9 a 11%. Pessoas respondem. PD1 ou CTLA4. Então, é um avanço, mas não é suficiente para realmente ter solução. Mas se você vai combinar checkpoint inhibitors, PD1, por exemplo, junto com vacina, você pode inibir a resposta que são inibidores e também estimular resposta específica contra aquele tumor. Então, essa tecnologia não é para tratar tumor primário, essa tecnologia é para evitar metástases, para evitar, para prolongar a vida. Próximo, por favor. Ok, então essa aqui eu estou querendo levar para o Brasil ano que vem, essa tecnologia anti-tumor. Depois eu posso discutir como vou fazer isso. Finalmente, outro tipo de RNA, a gente chama PAMP. Talvez você ouviu falar sobre RIG-I. RIG-I é um mecanismo que a célula usa para inibir vírus. Foi descoberto mais ou menos 10 anos atrás, eu não sei, por Michael Gale, em Seattle. Michael Gale faz parte da nossa companhia, ele é professor da Universidade de Washington. RIG-I é um mecanismo muito potente antiviral e antitumoral. E Michael identificou uma maneira de ativar RIG-I e ele chama a molécula PAMP. Nós vamos inventar o melhor nome, mas por enquanto chama PAMP. E nessa parte de apresentação eu vou falar sobre a promessa de PAMP. Próximo, por favor. Como nós somos expertos de formulação de RNA, Michael pediu a gente para ajudar ele virar a tecnologia PAMP para produtos que poderiam ser usados em vivo, não só in vitro. Como o PAMP funciona? Tem vários trabalhos publicados sobre isso, mas você pode ver aqui a revisão em Frontiers Immunotherapy, Immunologic, RIG-I receptors. RIG-I receptors as targets for antivirals and adjuvants. Okay? É uma grande revisão, você pode ver. E eu acho muito importante que você olhe esse trabalho, porque RIG-I vai ser um futuro, nem só para terapia, mas para adjuvante. Ele induz vários tipos de resposta imune, e você pode ver nesses trabalhos publicados, várias moléculas estimuladas, processos dendríticos, etc., para estimular a resposta imune eficácia. Próximo, por favor. Então, ele usa a resposta inata para induzir a resposta adaptiva. Bom, essa aqui mostra que como a gente começava a trabalhar com o RIG-I, porque Michael já tinha mostrado que ele inibe SARS, COVID, SARS, Hep B, influenza, RSV, dengue e febre amarela. Como vocês sabem, além de, fora de HIV, a gente não tem muitos antivirais. Tem uma coisa para influenza que mais ou menos, para HIV são ótimos, mas para outros virais tem poucos remédios. Então, realmente é uma biológica como isso que pode induzir resposta imune para controlar vírus, poderia ser muito potente, muito importante. Eu não falei no início, mas a HDT chama Host Directed Therapy. Nós estamos estimulando a própria resposta no hospedeiro para inibir o vírus, para criar uma resposta eficaz sobre contra o vírus, parte de vacina, por exemplo. Então, a HDT está baseado nisso. Próximo. Qual é o conceito aqui? Nós queremos fazer uma spray no nariz para quem testa positivo. Não é terapia, é uma post-exposure prophylaxis. Depois a pessoa testa positivo, o que eles fazem hoje? Eles voltam para casa esperar. Mas se você fizer uma coisa simples para introduzir no nariz, você pode imaginar que você pode inibir vírus para a pessoa não ficar doente e também ele não vai transmitir vírus para as outras pessoas. Esse poderia ser usado para influenza, para RSV e COVID. Próxima. Quase acabei aqui. E grande mercado, que hoje em dia tem mais do que 100 mil doses só nos Estados Unidos, testado, eu não sei no Brasil quais estados de teste contra o COVID, mas todo mundo que usa quem teste para detectar vírus no nariz poderia responder os dados positivos com esse spray. Mas, como eu já falei, eu estou muito interessado em usar para os outros tipos de terapia. Eu tomei a licença do RIG-I, do PAMP, do Michael, não por só vírus, mas também, eu não vou apresentar hoje, mas você pode injetar isso dentro do tumor, e o tumor vai desaparecer e ajudar pessoas a montar a resposta imune contra esse tumor. Porque, como eu já falei, PAMP funciona como adjuvante, além de funcionar como antiviral. Então, eu acho que o futuro é assim. Por exemplo, nesse caso aqui, se você tem vírus no nariz, RSV, influenza, SARS, se você bota PAMP, você pode induzir resposta imune, nem só tratar vírus naquela hora, mas para montar a resposta imune, para ser vacina natural. E a gente já sabe, com muitos estudos TLR3, em tumores, outro tipo de RNA, que você pode realmente tratar tumores por injeção. Mas, porque essa tecnologia nunca avançou, de novo, formulação. TLR3 teve muita promessa na clínica, mas produção era difícil, porque não é estável, mesma história. Ok, próximo, por favor. Ei, finito. Ok. Thank you.
A second. Here. Então, obrigada, Steve, pela apresentação, foi maravilhosa. Nós temos algumas perguntas. Rafael, quer fazer a pergunta ou eu pergunto? Rafael Freitas.
Rafael fez alguma coisa sobre autoimune, né?
Não, eu acho que tem outra pessoa.
Tem a do Isaac, desculpa. Ele perguntou, in addition to autoimmune response, what other risks or side effects are expected for this type of vaccine therapies, the RNA?
Autoimunidade, eu acho, não vai ser problema. Autoimunidade, porque depende de qual antígeno você coloca, né? Porque não tem vector. RNA não tem antígeno próprio de RNA. Então, autoimunidade, eu acho difícil você vai ter isso, problema. Por duas razões. Dose muito baixo, lembra isso. Então, não vai estimular a resposta muito alta. Você vai induzir a resposta que vai subir gradualmente. Other risks, side effects, desse tipo de vacina? Eu acho que muito menos do que outros tipos de vacinas. A terapia, eu acho que depende do hospedeiro. Por exemplo, boa pergunta, se você estimula a resposta imune muito forte, você pode ter efeitos colaterais, sabe? Mas a gente tem possibilidade de controlar isso por dose. Por exemplo, RNA, PAMP, por exemplo, ele induz a resposta inato. Claro, citocinas. Mas estamos usando dose muito pequena, então não estou vendo. Lembra, os problemas com citocinas, a terapia de citocinas, você está aplicando citocina direto. Muito interferon, por exemplo, muito IL-2. Esse é tóxico, o hospedeiro não pode responder na maneira, eles não podem aguentar esse tipo de coisa, mas quando você injeta PAMP, você está induzindo interleucina 2 ou interferon, então você está usando o controle do hospedeiro para controlar a quantidade de citocinas feitas. Então vai ser muito menos do que outras terapias, eu acho. Vamos ver.
Certo, obrigada. Rafael, passo a palavra para você.
Professor, é excelente. E a minha pergunta é se vocês também têm uma ideia sobre a indução de resposta imunicelular nos macacos e nos animais vacinados com RNA, e também se vocês têm uma ideia sobre a indução de memória nesses animais, se vocês estão fazendo um follow-up em termos de memória.
Excelente, excelente. Minha última companhia, Immune Design, eu usei uma tecnologia do David Baltimore, o que ganhou o prêmio Nobel para descobrir reverse transcriptase. E David inventou um tipo de lentivírus, alfavírus, para usar para terapia. E nós criamos uma companhia porque esse alfavírus induzia muito CD8. CD4 e CD8, mas muito CD8. Mas o problema com esse lentivírus, ou alfavírus em geral, é produção. E eles induzem a resposta contra o envelope do próprio vírus. Então, não pode ser usado muitas vezes. Rafael, eu estou animado com esse RNA, porque, por mim, eles representam o vírus artificial. Todos a vantagem de vírus sem a desvantagem. A CD8 é muito, muito potente. Nunca vi CD8 em macacos no PBMC, sangue periférico, induzido por só com adenovírus, mas nunca, com qualquer proteína adjuvante, nunca vi. Mas com isso, a gente tem. Não apresentei agora, mas temos CD8, CD4, como fosse um vírus natural. Primeiro. Segundo, memória, vamos ver. Mas é boa pergunta. Eu acho que o segredo de memória é IL-2, principalmente, e você não pode usar uma grande, alta dose de vacina. Então, uma preocupação que eu tenho, replicando no RNA, ele continua fazendo proteína. Então, uma preocupação que eu tenho, não pode usar muito, porque se usa muito, você vai começar a induzir IL-10, por exemplo, e menos IL-2. Então, memória, vamos ver, mas a grande pergunta, e nós temos que ver isso. Essa pergunta em geral, ou preocupação em geral que nós temos sobre vacinas no COVID, eles vão durar ou não? Mas vamos aprender. Mas boa pergunta.
Obrigado.
Obrigada, Rafael. Temos outra pergunta de Beatriz Oliveira. Essa aí você não conhece. Beatriz, pode ir.
Conheço. Beatriz. Oi, querido.
Olá. Primeiro, eu gostaria de agradecer ao professor Steve por aceitar o convite da gente. Muito bom ouvir você de novo. Espero que a gente se veja com mais frequência. Pegando o gancho do Rafael, eu queria saber do senhor se vocês esperam que esse tratamento em câncer, por exemplo, ele seria mais eficaz, no caso, em pacientes que estão em estágios menos avançados ou também serviria para já pacientes que estão com metástase, por exemplo, em estágios mais avançados de câncer? Como seria o tratamento nesse caso, utilizando essa nova tecnologia?
Bom, Beatriz, você precisa ter uma resposta imune, né, para poder usar essa terapia. Ideia usando pessoas menos avançadas ou pessoas em tratamento. Ideia, por exemplo, você tem várias maneiras agora de tratar o tumor, mas o problema, como você vai evitar metástases, como você vai evitar recrudescência. Então, se você tem uma resposta imune funcionando, deve funcionar bem. Mas para ter isso, eu acho que tem que tirar o tumor, se possível. E não é para tratar tumor primário, como eu falei, ela realmente era para prolongar a sobrevivência da pessoa. Esse é o grande problema. Por exemplo, câncer de mama, eu tenho uma colaboradora na Alemanha, ela disse que, bom, se a mulher expressa NY-ISO, um antígeno tumoral, e ela responde bem a NY-ISO, tem um anticorpo, por exemplo, eu posso prolongar a sobrevivência dela para 10, 15 anos, em vez de o normal, que é 5 anos, entendeu? Então, essa é a ideia, para continuar. E outra coisa interessante, nós aqui em Seattle, nosso amigo Paul Allen morreu de leucemia, ele não deve ter morrido. O problema é o tratamento que ele recebeu não funcionava mais porque mudou o tumor dele. Ele mudou, mutações, né? Então, com esse RNA, você pode responder imediatamente de mutações, entendeu? Você pode começar com uma vacina e depois, com o tempo, se voltar no tumor, você pode mudar para outra. Essa é a ideia. Prolongado de... para o preço razoável.
Pois é, um abraço em todos.
Obrigado.
Obrigada. Eu tenho uma pergunta também em relação a essa vacina de Zika. Vocês testaram em baixa dosagem também? Ela também era estável? Chegou a testar com outras boviroses, tipo dengue, que é um problema muito grande aqui na nossa região?
Não. Zika é uma... Zika talvez seria mais fácil de tudo, porque anticorpo neutralizante contra Zika é muito, muito potente. Então, usávamos 0,01 micrograma em camundongos. Não chegamos a fazer macacos. O Zika desapareceu e também nosso dinheiro desapareceu ao mesmo tempo. Mas eu estou realmente em conversa com Fiocruz no Rio para fazer Zika e febre amarela logo. Eu acho que, grande pergunta, realmente nós temos uma capacidade de criar uma vacina que realmente vacina dupla contra os dois, porque esse RNA, esse vector que a gente usamos tem grande capacidade. Você pode usar vários antígenos no mesmo vector. Mas eu sei que está voltando no Brasil. A ideia é começar já a produzir RNA no Brasil. Até hoje, nós temos colaborações no Rio e Salvador, mas nós vamos realmente ampliar essa rede, eu acho, para começar fazendo RNA em vários outros lugares, se vocês têm interesse.
So we have one lecturer that doesn't speak Portuguese, so I'm going to switch back to English, okay?
Sure, sorry about that. I didn't realize.
Oh, don't worry. We have one more question from Moacir.
Hi, Steve.
Hi.
Hi, great talk. It's just a
Thanks.
question because I'm working with oncology. So I'm going the same line as Beatrice. So my question is, we know that we have two different kind of tumors regarding inflammation response. Some we call cold tumors and the other ones we call hot tumors. So we already know that immunocheckpoint blockers is a success to the hot tumors, but not so successful with cold tumors. I saw lectures in AACR, I think 2 years ago. They are trying to give some vaccines intratumorally to enhance the antigenicity of the tumor and trying to better response after the immuno checkpoint blockers. And that time, the lecturers are talking about the peptide vaccines. And as you are talking about RNA vaccines, I would like to know if you have some news regarding vaccines, intratumoral vaccines, to enhance the immune response, mainly to treat these kind of tumors with immunocheckpoint blockers.
You have to, yes, absolutely. You may be talking about the Mainz meeting a couple of years ago, turning cold tumors hot.
Yeah, for sure.
It's a big topic. It's fantastic. Yeah. I didn't talk about this, but our other technology that we are developing and going to clinic with is called junction opener. So there's several ways to make a cold tumor hot. One of them is there's a protein that we called desmoglein 2. It's highly expressed in tumors that have a poor prognosis, and so we've developed a protein that can bind to desmoglein and create openings in solid tumors. And our first clinical trial will be ovarian cancer to deliver a drug to a tumor that's, because we found in women that have a high level of desmoglein 2, they have very bad prognosis. We want to decrease that level, get the drug into the tumor. But yes, we started the company to develop RNA therapies, both double-stranded, like Oncovir. You may remember Oncovir. Lots of clinical studies with that. It's a double-stranded RNA, but no formulation, very difficult to make, so it never went away. It never went very far. And the PAMP that I talked about, that's a single-stranded RNA. Both of those can turn a cold tumor hot. As long as you can get T cells inside.
Yeah.
You're absolutely right. We have to have a combination of methods and use them together with checkpoint inhibitors. So that's our passion, is to, whenever we can access a tumor, a melanoma, or maybe HCC, hepatocellular carcinoma, or maybe head and neck, when we can access that tumor, or even breast, we'd like to inject it and start creating an immune response internally. There are many papers that say turn a tumor into a vaccine. But these so they not only stimulate the innate response, they turn the tumor antigens that they see locally into a vaccine by inducing adaptive response. Oh, you're right, that's the future. Not just checkpoint, but checkpoint plus.
Yeah. Okay.
Just look at the website. We have some information on there, HTT bio, and then we can collaborate.
Okay, I will do that for sure. Thank you.
Okay, thank you.
So, Dr. Steve, thank you very much for your presentation and for contributing with us in these events. And I hope we talk to you soon. And I'm gonna call the next lecture now and call Michelle to do the next introduction. Thank you very much.
Prazer meu. Obrigado. Tchau.
Até mais.
Hello. Hello. Hello, Professor Zowling.
I'm going to listen.
Zowling, could you activate your microphone? Your camera?
Hello, can you hear me?
Hello, Professor. Thanks for being here. I'm very happy to be here in this first symposium with excellent lecture here. So if you could show your camera, you can. I would like to thank you, Professor Zowling, for have accepted our invitation. It's a pleasure to have you here. So I will speak in Portuguese about your curriculum, and I will back to you in a few minutes. So, Dr. Zowling é patologista e citopatologista, certificado pelo Royal College of Physicians. Dr. Shu current practice, pratica, né, patologista e citopatologista do Queen Elizabeth II Health Science, em Halifax, no Canadá. Ele também faz parte do departamento de patologia da Universidade de Dalhousie, em Halifax, Canadá. Ele fundou o Banco de Tumores de Pulmão em 2005, que se tornou o principal banco de tumores, né, do Canadá. Então, se tornou um banco de tumores de amostras tumorais referência no país. Ele tem sua linha de pesquisa voltada à busca de novos biomarcadores tumorais, tanto em tecido quanto em biópsia líquida, né, para traçar o perfil molecular dos tumores e buscar novas alternativas de terapia-alvo. E tem publicações em revistas importantes de impacto na área, né, que a gente destaca Nature, The Lancet Oncology, Journal of Thoracic Oncology. So I'm very happy, teacher. Once again, I thank you for being here to give us this lecture. So I pass to you. Thanks a lot.
Great, thank you so much for your introduction. Thank you all for inviting me for this session. And can you see the slides?
No.
No?
Not yet. You could.
Let me see how to
play in this bottom.
At the bottom, there is a thing that says present now.
Yeah, click that one.
And you have to present your full screen.
One window or
now.
That's nice.
Can you see now?
Yeah.
Oh, this one actually is not I would like to share. Sorry. No.
We only saw the screen of your computer, but the slides, no.
No slides. Just a second. Maybe my setting was not right.
Yeah.
So, Professor, there is some options when you press Show Now, and maybe it would be better if you choose the option entirely screen.
Yeah, maybe I try it again.
For sure. Well, Professor, if you want, you can send your presentation to Michelle, and Michelle could share your PPT with us.
Yes, could be.
So can you share my screen? What's going?
I have my email here. If you could send me.
So maybe you can try to stop your transmission and then restart again.
So can you share my screen? I have difficulty to share my screen.
Hi, Professor. On a device, if you want to just come in the room again, maybe it will be easier for you. Then you can just okay. Yes.
Juan, aceita ele, pelo amor de Deus.
Vamos aguardar um pouquinho, pessoal. Ele não enviou por e-mail. Acho que ele vai tentar entrar novamente.
Se ele conseguisse enviar por e-mail, seria melhor, né?
Sim. Eu estou com o e-mail aberto, mas ele não enviou ainda.
Entrou de novo.
I tried again. Sorry about this.
Sim.
Can you see slides?
No, only the computer.
Just a second. Yeah, because I have 3 screens in my my office. That's a confusion. You can see what? Oh no.
No. Yes, the log of Windows.
Maybe I try it again. Can you see the slide?
No.
No.
Maybe it's better that you send the email to Michelle with the PPT file. Could be.
So sorry, what's that?
Could you send to Michelle the email, an email with your presentation?
Sure. Maybe
Yeah.
I email. How about that?
Yeah.
Sorry about this.
No problem.
No problem. I could receive here now and open.
Oh, because the file is too big.
Too big?
The file is too big to send.
Maybe in PDF file?
What?
In PDF file, I guess will be also okay for Michelle share
So
screen.
that's PowerPoint.
Yeah. Did you try a screen or only window when you show a presentation?
So who else is sharing? Maybe someone can stop sharing.
Yeah. Try your slides now.
Huh?
Try your slides now because we're seeing your screen.
Do you see my screen?
Yes, try to put your slides now. Maybe we're gonna see them.
Yeah, I already put my slides on.
Oh.
But someone else sharing the screening can stop the sharing, discontinue sharing.
Yes, I can see you continue sharing. We can see it.
Hey,
we can see the Zoom, the Meet screen.
Yeah.
But you cannot see the slides. Put PowerPoint slides, can you?
No, not yet.
Details.
Just a second.
It's strange.
Does not allow me to share in the screening.
Window. The PDF of your presentation, would you try to send me? File.
Yes, now we can
see.
So you can see the slides?
Very nice.
Yeah, you can see the
I'm sorry about this, but there was a confusion. I have three screens in my office, so that's why I have a difficulty sometimes. I don't know which one to share. Anyway, thank you so much for inviting me. The talk is Advance of Pathology in Modern Oncology, especially using lung cancer as one example because I'm a lung pathologist. And this is my disclosure. This is a percent distribution of Canadian cancer deaths by sex in 2019. The top 3 cancer deaths for male is lung, colorectal, and prostate cancers. For female is the lung, breast, and colorectal cancers. And look at the Canadian data, 225 and 800 new cancer diagnoses and 83,000 deaths was predicted to occur in Canada in 2020. Cancer is still the leading cause of death among all other causes. 1 in 2 Canadians will develop cancer, and 1 in 4 will die of the disease. And the lung, colorectal, breast, and prostate cancers accounted for almost half of all new cancer cases. Lung cancer is still the leading cause of cancer deaths in both male and female. This data probably pretty much similar in many countries. And the 5-year survival based on 2012 to 2014 data, lung is 90%, lung cancer 90%, colorectal 65%, breast 88%, prostate 93%. This is pretty much data similar as the United States and some European countries. This is a proportion of deaths due to a variety of causes. You can see cancer-related deaths has the highest proportion, accounting for about 30%, and followed by heart disease, which is about 20%, and then I have a chunk of cases as other causes combined. As you know, staging status is the single most important prognostic factor. This is a percentage of lung cancer subtypes in various stages. A yellow bar is a stage 1, beige stage 2, light blue stage 3, dark blue stage 4. You can see a vast majority of cases at the time of a diagnosis is already in stage 4. That means in the advanced stage. And in lung adenocarcinoma, stage 1 is about 26%, while stage 4 is almost 50%. In order to treat cancer, a patient's diagnosis of the disease is vital, especially pathological diagnosis. There is no single event that demarcates the beginning of the pathology as a defined area of medicine. In fact, the history of pathology has roots in common with all other medical subspecialties. Documentation of disease begins with Egyptian medicine about 17th century BC or earlier. Zacharias Janssen was a Dutch spectacle maker who was the one to invent the first optical telescope, and was also considered as the invention of the first compound microscope. Rudolf Virchow is a German doctor who was also an anthropologist, pathologist, biologist, physician, and also a writer, editor, and many titles. And he was regarded as one of the greatest figures in the history of pathology. And his contribution was made the pathology become very, very important for the diagnosis, and developed many things by his contribution later on. And you can see initially was looking at the growth of lesion on the body to make a diagnosis, eventually go to microscope, make a diagnosis, and the microscopic diagnosis is still the main methods, one of the main methods to make a diagnosis nowadays. In order to make a diagnosis and treatment, the cancer classification becomes very, very important. And then there are two systems. One is a histological classification, one is a TNM classification. The first one is based on the histological type, primary site, and the location. The second classification is to deal with extent of cancer and the prognosis. And most institutions using WHO classification for cancer diagnosis. Here's the lung cancer, the WHO classification. First, one edition was the early edition was in 1967, and the latest was published in 2015. And you can see that the classification changes, and because new information available at the time. And this is adenocarcinoma, and you can compare the different versions of the classification. And here the squamous cell carcinoma, and the changes of classification. This is large cell carcinoma, and now the comparison is 2004 edition, and the 2015 edition becomes simpler, just one entity, one category, and then for 2004, have several. And here the small cell carcinoma and the different subtypes. And there are some new entities add on, and because of new discoveries. One example is nut carcinoma, which is a very aggressive tumor, usually in the middle line or occur in the thymus, but it is also included in the lung cancer category. It has a gene rearrangement translocation 1519 or 159. And the histology, it is sheets of cells, monomorphic small to intermediate cell type. And in order to make a diagnosis, probably you need an antibody against the nut. Then, of course, if you do the other stains, it is positive for cytokeratin, positive for P63 or P40, and the CD34. Sometimes positive for neuroendocrine markers or TTF1. That's why it causes the confusion by the diagnosis. Many of them misdiagnosed as small cell carcinoma, but this is a new entity add-on in the 2015 category of the WHO classification. And the other system I mentioned is TNM staging system. Now everyone using international TNM staging, and that actually by two versions. One is AJCC, stands for American Joint Committee on Cancer. The other is UICC, stands for the International Cancer Control. But these two organizations produce identical classification, but that published by two different organizations. The latest one is the 8th edition. Probably you are using the same classification as well, effective in January 2017. And the comparing with the previous one has some modifications and listed here. For example, previous one, there was no T1C category. Now it's become a T1C. This is all based on the clinical data and the reasonably to separate them rather than combine together as the previous one. And everyone using the same classification for staging of the cancer. In such a case, then one case diagnosed in one site or one country can compare with the other site in other countries. Then everyone uses similar criteria to staging the disease status. And as you know, the staging is a status is one of the most important prognostic factors for cancer diagnosis or cancer prognosis. So besides these more microscopic examination, and electron microscopic examination was very popular in 30 and 40 years ago. It is able to provide additional information to assist diagnosis, and many diseases can be confirmed through electronic microscopic examination. Here are some examples. The left picture shows short microvilli, usually seen in adenocarcinoma. The right picture shows a long, slender, wavy microvilli, and it is a characteristic appearance for mesothelial cells. And if you want to make diagnosis of mesothelioma versus metastatic adenocarcinoma, a microscopic, electron microscopic examination can provide some information for confirming the diagnosis. The left picture is neurosecretory granules, these black dots, and is a characteristic appearance for neuroendocrine tumors. And the right picture is called the Burback granules, and like pentalaminar rods, like a structure, and like tennis rackets, like appearance on like this. And it is a characteristic changes for Lancan cells. And if you want to make a diagnosis of Lancan cell histocytosis, and the EM can provide the confirmation of information for you, and you can make a diagnosis once you find these structures within the cell. This is a melanosome, this one, and these are in lower magnification. And this is characteristic changes for melanocytic cells. If you want to make a diagnosis of melanoma, and if you do the electron microscopic examination, and you can find these structures. However, electron microscopic examination was replaced by immunohistochemistry lately, and because immunohistochemistry is a quick, cheap, easy to do rather than electron microscopic examination. And it is the most common application of immunostaining, which involves the process of selectively identified antigen in cells of a tissue section by exploring the principle of antibodies binding specific to antigens in biological tissue. There are different types of immunohistochemistry. Popular one is we call the ABC type, and is an avidin binding complex method. It is a standard used in many labs, and you have a primary antibody targeted at specific antigen on the tissue. Then you have a secondary antibody. Then you connect to avidin binding complex, and it shows the color. And this method, LSAB, is similar as ABC, and but the more simpler for the complex and more sensitive comparing with ABC. The more popular nowadays is called the polymer or polymeric method, which is using a polymer backbone, and there are lots of enzymes attached to this, and it is reduced background noise and is a more clean staining. And this is in the our lab. This method probably replaced all these two methods. Nowadays, is a very popular methodology to use. IHC is mainly used for helping to make a diagnosis based on organ or cell type specific antibodies. And here are some examples. For example, TTF1 NEPS-A are positive in bronchogenic adenocarcinoma. About 70 to 80% cases were shown. And that means positive is helpful, negative you cannot rule out. But the TTF1 will also occur in thyroid cancer and in some of the other cancers. And P40 in the CK5-6 indicating squamous differentiation. Now you have another example, other examples for different cell types. And another group of antibody used for IHC can be a predictive value and able to provide indication of a likelihood of tumor response to giving treatment. So example is a targeted therapy, and if you're using these antibodies, you can give a predictive value. Currently, immune checkpoint assessment with immunotherapy is a hot subject. Programmed cell death 1 also called the PD-1, is an immune inhibitory receptor of the CD28 family, which is present in immune cells and play a major role in tumor immune escape. Its ligand, PD-L1, is present in tumor cells. And so PD-1 in immune cells, PD-L1 in tumor cells. And the PD-1, PD-L1 interaction inhibits T cell function, and then inhibit the immune response. And then if you have a compound block the PD-1 or PD-L1 interaction, either way, you can binding this or you can binding this, block that, and it will resume immune response. And that's how nowadays the immune therapy is mainly based on. And the two scientists, one is from United States, James Allison, and the other from Japan, and their contribution for immune therapy, especially they are not dealing with killing the tumor cells. It basically is a modification and change the immune system itself, result in cancer treatment. They win the Nobel Prize 2 years ago. And there are also other antibodies can be a prognostic, have a prognostic value, and it's listed here. Them indicating how the tumor's clinical outcome would be if you have things like this. So what do we learn from the history? We know surgical treatment is effective, but that has limitations. A majority of lung cancer cases with no surgical indication at the time of diagnosis, as I previously showed, more lung cancer cases diagnosed as stage 4 at the time of a diagnosis. So the loss of opportunity for surgery. Chemotherapy and the radiation are mainly palliative. So the solution in one is prevention, one is early detection, the other is new modality if we have. Traditionally, tumors have been assessed and categorized on the basis of histology. However, microscopic examination does not reflect the complicated underlying molecular events that drives the neoplastic process. By surveying thousands of genes at once, it is now possible to read the molecular signature of an individual patient's tumor. Using DNA arrays, protein arrays, and appropriate experiments, new insights into disease mechanisms and the identification of new treatment targets can be achieved. Mutant genes responsible for cancer development and growth are known as drivers. And many targeted drugs are tyrosine kinase inhibitors, which are able to treat cancer harboring the driver genes. Here's some list, and you can see many of them, they are identified. And in Canada, we have a national initiatives in that direction. And for example, in 2011, and there was a pan-Canadian ORC study in trying to work together to make from the lab point of view how to make a diagnosis of ORC. Usually it's by IHC plus minus FISH, and try to get a validation across Canada. But the reason is the percentage of ORC positive cases are very, very low. It is difficult for each individual labs to do a validation. And take the same approach. 2016, we did a pan-Canadian ROS1 study, and do the same approach, IHC plus minus FISH. Then we have a PD-L1 validation in 2017, and then now we're doing a CAN-TRACK ring study, trying to do NTRK identification by IHC and plus minus NGS. So lung cancer molecular profiling, our site, we're in Nova Scotia, in Canada, and in 2012 we take approach of multiplex the molecular profiling, and then at that time was testing the EGFR, KRAS, BRAF, PIK3CA, HER2, and ALK, and at the same time, and we do a true reflex testing. That means that no matter clinical staging status, as long as we make diagnosis lung, it is a lung adenocarcinoma or non-small cell carcinoma, favor lung adenocarcinoma, the molecular profiling will be initiated right away, rather than waiting for the medical oncologist request, because in such a way, save time, save resource, and do these genes at once. Now in 2017, this is a PCR-based, regular PCR-based, and in 2017 we switched to next generation sequencing, NGS, and more gene was added, and we were using a Illumina TrueSight 15 gene panel, and these are genes listed. And this is for lung adenocarcinoma. And the ALK and the ROS1 still using IHC and the FISH, but for the safe resource point of view, and once the molecular profiling shows negative when we add these two, the reason is that these drivers are usually mutually exclusive. And if you have an EGFR mutation, for example, then you unlikely you'll have an ALK mutation or ROS1 mutation. So that's why these genes probably can identify in half of the lung adenocarcinoma. So in that case, we just save half of the cases and not doing ALK and ROS1 because we're the reason I just explained. And probably we have 8 to 1,000 cases each year for testing. And for our in-house, that means because we receive a consultation from outside as well. But in our own institution, the unsuccessful rate for molecular profiling is only 2%. It is very low. It is very good results, and usually it's 10 to 15% for if you look at the literature. But we only have a 2% because of the way we're dealing with is we have our own way how to deal with tissue. And this study was one of the graduate students to work with me, and then did a study. We evaluated 1,044 cases of lung carcinoma. Then this is the demographic information with the staging, with the cancer subtypes. And then if you look at the data, the top left, this one is each mutation type in entire cohort, including adeno and squamous carcinoma. This is a study we testing a non-small cell carcinoma. So the KRAS is the highest, 28%, and EGFR was low, 7%, as opposed to the literature probably 10-15%. But if you divide it into squamous and adenocarcinoma, then differently, then and this is a positive rate increase. Therefore, EGFR positive rate increased to 11%. And this is a KRAS mutation on this side. Sorry, so this is KRAS. This is EGFR. Sorry. And these are all for the entire cases. Then the KRAS mutation, and you can see there's a mutant is very high, and there's a non-mutant because of we separated, stratified. And then if you look at the EGFR mutation comparing to PD-L1 testing, the PD-L1 divided into 3 groups: less than 1%, 1 to 49%, and more than 50%. We are talking about the tumor proportional score, TPS. Then the EGFR has the lower cases in less 1%. That is the mutant. This is a wild type. And this is similar for the KRAS cases. You can see here. And there's a difference of the EGFR and less EGFR mutant cases seen in the less than 1%, and but for the just a second, let me see. So sorry, this the red bar is a mutant, and the blue bar is a wild type. So in the EGFR mutant cases, and the less 1% PD-L1 TPS less 1% is more cases, and comparing with the KRAS, and as a reverse has less cases. The top left is how old of the tissue blocks affect the PD-L1 testing, and you can see two groups. One is 2016 and above, and one is 2017 and 2018. That means in the recent 2 years was in the red bar, and the older one was in the right in the blue bar. And you can see the older blocks shows more or less 1%. That means less PD-L1 expression if you're using older specimens. So be aware of the phenomenon like this. If you want to testing all the cases like 2 years earlier, and the chances for PD-L1 expression were reduced, and the data shows that. And the bottom left is smokers and the never smokers, and still is 3 groups. One is the less 1%, one is 1 to 49%, and one is more than 50%. And blue bar has a smoking history, and the red bar has a never smokers. And the never smokers has a high percentage didn't show PD-L1 expression comparing with the smoker patient. And looking at the different groups and grades, for example, grade 1, grade 2, grade 3 for the tumors, and then still is 3 groups: PD-L1 less than 1%, 1 to 49%, more than 50%. And then in the lower grade, that means grade 1, shows more people is less 1%. That means the PD-L1 not expressed. And then if grade 3, then the poorly differentiated has a less PD-L1 less than 1% compared with the grade 1. But the staging status, there was no statistical significance. So future direction, probably we're going to not like many centers only testing one gene at a time, and you should use a larger panel. In 2012, we're using 6 genes at testing together. 2017, we're using 15 genes, and now we're using 52 genes. So the larger gene testing at once, and you save time and save results. You can test it at once in the very beginning and get the information you need. And so this, as I mentioned, the currently we're using this, and we're going to using this currently we're using a two-sided 15 gene panel, but we are going to using 52 gene panel to replace the 15 gene panel shortly. And then you can choose the panel from different companies like here. And another direction is the liquid biopsy. Liquid biopsy is a very important. I think it will be one of the future directions for molecular profiling. The reason is you use a tissue to make profiling. Currently, we're doing, but in some cases, the patient is not able to do a tissue biopsy, especially when they get recurred or your more advanced stage of patients. So you test in blood and you test in the gene mutations. Probably it will provide you useful information. And the same, another direction is a centralized tumor bank. A tumor bank is very important because you can do lots of research for tumor bank. This is a workflow for the tumor bank, and initially with the physician talk to the patient, sign the consent, then about the operation, and specimen will send it to the lab right away. The lab will process and do the microscopic examination, and at the same time take tissue for the put it into the snap freeze, then put in the minus 80 deep freezer. And then once you had the diagnosis, and then you can do the tissue marker array, and then everything is put in the computer, stored, and then you can add on the clinical information in as well. And then you become tumor bank information. Actually, in Canada, there was a Canadian Tissue Repository Network, CEDARNet, which is based in Vancouver, British Columbia, in Canada. There was a well-designed way how to process and do the tumor bank, and they provide guidelines, and then eventually you can get a certification from them. We have our own lung tumor bank, and currently have 1,240 cases collected in tumor bank. These are surgically resected specimens, large specimens, not biopsy specimens. So we have H&E slides and the paraffin blocks. We have a tissue marker array with frozen tumor tissue, match the normal lung tissue from the same patient, match the blood and the plasma tumor tissue in RNA later for RNA extraction later on. We have a DNA extraction from the blood. We have a DNA extraction from the tumor for the one case. Then at the same time, we have a data collection. We have a demographic and clinical data, including survival data matched. They have a pathological data like diagnosis, staging, and classification. And all of these have a molecular profiling, as I mentioned, same as I mentioned before. Then we have a PD-L1 data for all of these cases. So this is a very comprehensive tumor bank, and it is the most comprehensive lung cancer tumor bank in Canada. Then, of course, you have bigger data collection and sharing. This is very important. These are the Cancer Genome Atlas, and then you have a Human Genome Project and the tumor banking, SNOVA reporting, and others. And this is now you can get more and more data to analyzing and do collaborations. And artificial intelligence now is becoming a very hot area, and it is so important. In order to the artificial intelligence, you need a high speed equipment. For example, 5G. This is a next generation of mobile broadband with a very fast download and upload speed, and because of speed is so high and then so fast, then you can do many things. And there is a 3 band, and the low band spectrum probably is 100 megabytes per second. And you have a medium band spectrum is about 1 gigabyte per second. Then you have a high speed, probably up to 10 gigabyte per second. And but the high speed probably less penetration. So you probably need to sell a small equipment in many places. Otherwise, you cannot receive the signal. The usage of these ones, for example, improve the broadband and for the communication and autonomous vehicles. It is already on the market, in the public safety and the infrastructure and remote device control. For example, you do a remote surgery, and you can control by far away, but because the speed is so fast, then one side makes signal, the other will make action immediately. And the internet, many other things, it is needed. Now, besides this 5G, now I have a 6G is on the way, and in the near future, 6G is the newest generation of wireless communication technologies. The speed is about 95 gigabyte per second. And the 5G highest, you go to 10 gigabyte. Now it's 95, almost 10 times faster. And commercially available around 2030. not now, but now is exploring. And actually, I look at the news a few days ago. 5 days ago, China successfully launched the experimental 6G testing satellite. And this satellite is to verify the terahertz communication technology in space. So artificial intelligence examples, in 2005, you can see I published a paper about artificial intelligence that could learn a human level control the games. Probably you all know the AlphaGo beat the professional Go player 4-1 in 2016. You can see how powerful of the artificial intelligence. And AlphaGo 0 could beat AlphaGo with more than 90% chances. And then eventually the humanoid robot and play the rules in our society. So there was many applications for artificial intelligence in pathology, for example, to deal with genomic and biological problems, and can reduce the diagnostic variabilities and can control. And again, digital pathology can be available, and now it's available, but they become more and more accurate, and because the speed increases. And the cancer subtype determination, currently we are subtyping with based on our eyes. We look at the microscope, and the microscope can make a grade. But there was an error, and if you use the machine to do, and probably more accurate, as long as the machine was trained. And then the automated reporting, and then centralized reporting, and home reporting, and the experts reporting. These all will be available once the artificial intelligence become more and more practically can be used. And for example, one side, actually you don't need many centers, you don't hospital, you don't need a pathology department. You can prepare slides automatically, then scan the images, send it to central lab, and the experts sitting there, they can read at the same time, and can reporting, and very can efficiently do the job as currently we are doing as a routine. So artificial intelligence will play the more and more major roles in our society, and the time will come, and we have to prepare for the new era. And so that's all what I'm going to talk. Thank you so much. I'm sorry about the delay in the beginning because of problems with in my end. Thank you.
Thanks, Professor Zhao. Someone have any question for Dr. Zhao? I have one, Professor. You talk about early detection. That's the mainly problem to detection of lung cancer. So do you believe that we will find this early screening biomarker for lung cancer? Do you believe that we will find a biomarker to identify early detection?
So early detection, I'm not sure in Brazil and in Canada with started many years ago, but actually put in practice only still in a pilot study. The main reason was for the funding issue, and if you do early screening, and you need a lot of money to support, and because you screen the population initially was not doing the CT, now you are CT, and it gave a lot of burden to the health system. Canada is like public health. Everything was paid for by the government. So that's why the slow down a little bit. And so I don't have a much screening cases to be able to draw a conclusion whether or not early detection identify the lung cancer, whether or not molecular profiling is different from the clinical setting. I don't have the data, so I'm not able to provide the answer to that.
Yeah. Okay. I can ask something, Michelle, if you have time. I'm not sure if you have time. Yeah,
Sure.
probably. Okay. So thank you very much, Professor, for your talk. It's a work with tons of effort. So congratulations on that. It's a really, really nice work that you have done so far. Actually, it's in the flow of Michelle's question. As you talked about artificial intelligence, a question came to my mind because a newer robotic bronchoscopy platform that allows just to see not allows just to see the lung nodules, but also reach lung nodules without invasive surgery has been developed now. It's a 3D models of the patient's own lungs anatomy, let's say. And do you think that there is a genetic inducible molecular alteration in lungs before even the appearance of the nodules or the symptomatologic issue? And you think that these platforms, I mean, genetic platforms and also this robotic platform can be combined to enhance the lung cancer diagnostic and maybe in the future another kind of cancers as well?
I think that's a good question. We try to, as I mentioned before, for the cancer treatment, any type of cancers, if for the improving prognosis, one of the best way is early detection. There's one of them is early detection. Whether for the early cases you treated, and probably you have a much better prognosis. But using artificial intelligence and with molecular profiling can provide very useful and helpful tool to reach the cases currently we are not able to identify, and then the treatment based on this probably will yield a relatively good prognosis afterwards. And one of the important thing is we're still trying to search whether or not early, same as the previous question, we're trying to search whether or not early stage of the lung cancer, the molecular profiling is different from the later stage. Based on the data I have, I showed one of the slides because I speak past it quickly. I just mentioned one sentence is there is no difference between the early stage 1 to stage 4 for the prognosis point of view, and of comparing with the molecular profiling as the data we have. However, this is only a small set of cohort, and we're still searching to see whether or not there was a subtle difference. And it is actually one of the interesting question and the topic. And not only me, probably many people in that area were trying to search.
Okay, thank you very much.
We have another question. What do you think about less invasive biomarkers such as the plasma prosulfurtant protein B for early detection and or prediction of lung cancer?
So which marker you're talking about?
It's a question.
Sorry, I didn't hear you.
Prosulfurtant protein B. We have this question in chat. A question from Pedro Souza. I think he asked about liquid biopsy used in early detection. And so he cited this example, the prosulfurtant protein B for early detection. What do you?
That one was I do not know, and because currently the panel for the clinical usage, and we know the drivers, and if you do a next generation sequencing for lung cancer, you can find many genes, and they are not appearing in the normal tissue, for example. The problem is we do not know some genes, what the role of these genes, we do not know. And currently we know the genes, for example, I mentioned like EGFR, ORG, BRAF, KRAS, HER2, PIK3CA, NTRK, and MET, for example. These we know these are drivers. Many other genes may or may not be a driver, so we do not know. Having said that, it is very important to explore, and many scientists, they are doing the experiment trying to find the new genes. And once you find the new genes for gene mutations, then you have to verify these genes, what the role of these genes in the cancer development. And once you prove this is one of the new drivers, then you made contributions for the area, and then it is very important. But as I said, many genes we can identify, but the genes, the rules of the genes in the cancer, we do not know. So for the particular gene you mentioned, I do not familiar with, so I cannot answer the question.
Yes, there are a lot of big data to be investigated in lung cancer. And so I think we don't have any time to more questions. I would like to thank you again, Dr. Zauling, for being here with us. Thanks.
Great, thank you. Thank you all.
So our next guest is Dr. Laura Chamber. She's already there. Hi, Laura.
Hi, nice to meet you.
Nice to meet you. Thank you very much for accepting our invitation to participate in the symposium. And before you start, I'm just going to read your CV in Portuguese very quickly, and then I can pass the word to you. Okay.
That's good.
Então, pessoal, boa tarde. A doutora Laura, ela tem um bacharelado duplo na universidade na França e nos Estados Unidos, que é a Therapeutic. Ela tem mestrado em Química Orgânica, em Síntese Orgânica, também pela Therapeutic, e depois disso ela teve uma experiência do seu doutorado em polímeros terapêuticos na Universidade de Bogazici, não sei se está certo, em Istambul. Atualmente, ela trabalha no Departamento de Engenharia Biomédica da Universidade de Tufts, onde ela é pesquisadora pós-doc, e ela gerencia e executa pesquisas inovadoras com financiamento de vários tipos de agência nacional, em colaboração com universidades e com empresas, nessa parte de utilização de seda, né, para entrega e estabilização de medicamentos. Também trabalha na blindagem de medicamentos para missões no espaço, com financiamento da NASA, e vem trabalhando em diferentes construções, como espumas, reservatórios, filmes, com o objetivo de fazer uma entrega sustentada e controlada e também prolongada de medicamentos, tanto quimioterápicos quanto medicamentos de uso como antibióticos e etc. A doutora Laura, ela tem várias publicações nessa parte de química de materiais, visando, né, o melhoramento da saúde humana. So, Laura, thank you very much, and she will be talking to us today about silk-based biomaterials. Thank you, Laura.
Thank you so much. Can you see my screen okay?
Yes.
Okay, great. So today I will be talking to you about silk-based biomaterials for drug stabilization and drug delivery. So as you probably mentioned in Brazilian, I'm doing my postdoc in the Kaplan's lab at Tufts University. I started almost 2 years ago, and I've been focusing my research on, as mentioned in the title, drug stabilization and drug delivery. So the whole Kaplan lab, I would say 90% of the work or more is all based on silk. And usually when people think about silk, they're thinking about textiles, scarf and tops and things like this. But here it's all biomedical application. So silk is a high molecular weight protein, which is amphiphilic. So it has some hydrophilic linkers, which is the light chain, but it also has some hydrophilic repeats, which is the main component of this silk fibrin fibers. And this protein has really great properties. So it's a really robust materials. It has a lot of chemical handles thanks to the different amino acids that compose this fibroin. And also, you can have some inter-chain crystal, meaning beta sheets, that can help you with this robustness of the material. So all those properties of the silk makes it a really great handle for stabilization. And this is, if you see on this graph, so you have your macromolecules here. And if you embed it inside silk, you're going to have protection coming from the beta acid region. You're also going to have the amorphous region of the silk around. And this will prevent, so it will have a low water content in the nanodomains, but it will prevent excess water. It will also immobilize your macromolecule in this reduced conformational mobility. So it will be in this frozen state, which is the native and the optimal conformation. We can also stabilize and modify the stabilization and optimize it by manipulating the submaterial properties. So whether we want to increase or decrease the beta sheet formation. So all of those handles of the silk makes it a really great compound for stabilization. So first, the first talk that I will give you are about a study that have been published about stabilization. And then later on, we will go about drug delivery. This is to show you the different format that we can use for the silk. So which is also a great attribute to silk is you can have implants such as tube, rods, porous scaffolds, so like cryogels. You can have injectable things such as cryogel can also be injectable, but hydrogels. You can have microsphere or nanoparticles, and you can also have transdermal constructs such as microneedle for transdermal delivery. So all of those will be obtained starting from those silk cocoon that you can see here. Those cocoon are then degummed. And so by degumming, you are removing the sericin protein and you are left with the fibrin fibers. And then these fibers, you're just dissolving it and dissolving it and you obtain this aqueous solution. And this is starting from this aqueous solution that you can form all those different constructs based on the application that you want to use it. And the key features of the silk is that first, it's long-term release, and silk is biodegradable, but based on its property, it's going to degrade between months to years. So again, you can play on the properties for depending how long you want to use it for. Also, it doesn't induce any immune response. So this is another great factor of silk. Here we are showing some of the different parameters we can use for the silk. So once you have your cocoon pieces and you're going to degum them, we actually use a salt and some boiling water to degum it and remove the sericin. And based on the time that you're going to boil the silk, you're actually going to obtain a different molecular weight. So the longer you're going to boil the silk, the lower your molecular weight. And so if you start with something more robust, so just like, let's say a 10-minute boil time, it's gonna be great for robust film. Then if you have a 30-minute boil, it's gonna be better for scaffold fabrication. And then if you go all the way to 60 minutes, it's gonna be better for things such as stabilization and recovery. I would say that most of the study we are doing actually with 30 minutes boil. And if you want to stabilize antibodies or drug, we actually use lyophilization. So once we have our liquid silk that we can mix with the drug that we want to, then we can just lyophilize it and keep it for storage for day, month, year. And then once you want to put it back in solution, you just add a water solution. And the graph at the bottom is just showing you the silk concentration that you can obtain, like the solubility based on the boiling time, so molecular weight and the amount of it. So as you see, the 60-minute boil, which is the lower molecular weight, will have actually, you can reach a higher concentration. This is just to show you kind of the mechanism of stabilization, but similar to what I've just talked about. So if you want to stabilize your drug or protein, antibodies, so you're just going to have your silk solution and your biologic that you're going to mix in water, in this silk fibrin water that you have. And then you're going to lyophilize this solution or just let it dry in the air. And you can obtain different formats. So you can keep it as a freeze-dry powder, you can spray dry, you can do 3D printings, sponges, gel, film. And the glass dynamic of so thanks to the beta sheet from the silk, it's going to suppress the mobility of your drug or your antibodies. And so it's going to decrease any protein-protein interaction and also prevent any degradation. And this can be used for storage, like I mentioned, for day, month, or year, and even at elevated temperature. So think about if you have a vaccine and you know how you have to keep the cold chain, especially right now they're talking for COVID. So they just found out this new vaccine that is 90% effective, but then it needs to be transported at minus 80 degrees, which is really cumbersome. But if you have like a stabilization process such as silk, then you can avoid all this cold chain. And it's actually a couple of companies now that are working on this. And once you want to have the drug out after the storage, just by hydration, by adding water, or by being applied to the skin, then the drug is going to start to come out. So another really interesting project that we are working on right now is related to, so we wanted to see like how is silk going to react in space. So, you know, NASA is planning to send new people to the moon by 2024 and later on go to Mars soon. So in I believe more than 10 years ago, they sent some silk sample to the ISS. So the sample stayed on the space station, I believe, for 18 months. And you can see here on the panel C, so this is where you are your silk films, and on panel B, this is how they are. So they're actually outside in the space, and you can see in the pictures here. And so this ISS is in the low Earth orbit, so it's not similar to the Mars environment, but you still have some ionizing radiation, so X-rays, gamma, cosmic radiation, and you also have some non-ionizing, such as light, microwave, and radio wave. And so when they get the sample back, they wanted to see how are they looking. And so they sent some just regular silk, silk with silica, and also collagen that I didn't include here. And what they've seen is that if you look at the space travel silk compared to the Earth silk, so our control in that case, you can see all the surface by the ECM, which is kind of eroded. And we also noticed that 80% of the silk column was chemically crossing by the space radiation. We also see some effect when they were O2 ion treated, so this was done on Earth. And you also see some etching and some erosion of the surface, but not as bad as the space travel one. And finally, in the last one, they added this inorganic particle, so silica in that case, and they see the surface is actually much better. And what they're thinking is that the silica acts as an efficient excitation energy sink, so it's kind of absorbing all the radiation in the space, protecting the silk from radiation that can occur over there. So based on those results, we started this project funded by NASA actually when I arrived at Tufts, so January 2019. And so what I wanted to see is, since we know silk is great for stabilization of medication, and as well as the for the radiation wave silica, so they wanted to see whether we could stabilize medication once for the astronaut that goes to space. So if you go to the ISS, they can bring medication, or they can have it there, and the travel is not that long. But for the crew member, we'll want to go all the way to the Mars. It's going to take, I think, the round trip, it's 2 to 3 years. So it's much longer. And also you have a lot of different radiation. So when you go to Mars, once you exit the low Earth orbit, you're going to have galactic cosmic radiation, you're going to have solar particle events, and all of those radiation are much higher than in the lower Earth orbits. So they wanted to see, well, if we put silk with our medication, can we actually protect the medication so they don't get degraded, first of all, by the radiation, and also they can go past their date of usage. So a couple of studies has been done before where they actually took the medication by themselves to space, and some of them were stable, some are not. So if you see in red, those are all the medication that were non-stable. So we decided to focus our study on 2 drugs for now. So ampicillin, which was, I don't know if it's in that list, but it was shown to be stable. And the other one, clavulanate. So clavulanate is mixed with amoxicillin, and it's a medication called Augmentin, which is an antibiotic. And also on top of that, if we can use silk, we can also decrease all the packaging. So right now, all the drugs are either stored in their native, like packaging, or they are put in polypropylene bottles, because polypropylene are known to also absorb the radiation. But the thing is, this takes space, and you can see the picture here. And if you go to Mars and you need to take all those medications for 2 years or 3 years, you want to minimize the storage and the weight. So the goal of the study again, so we wanted to take the silk solution, add some additives such as glycerol, which is known to kind of plasticize the silk, silica, which I showed before, that was acting as a sink for the radiation, as well as vitamin C or Trolox. So those are two antioxidants that could help also preserve the medication. And we wanted to focus on two different formats. So either silk drug films, where you actually mix the medication with the silk, and then once you're ready to use it, you just swallow it and the drug will slowly diffuse, or we can do a silk drug pouch. So you have two silk films that you press together and the drug is actually in between, and then you can just cut it open and get the drug. So we focus mostly on the silk drug films for this part. And what I did is last month, I went to the NASA Space Radiation Lab, which is located in Brookhaven, New York. So this is actually the only place in US that you have such high radiation. It's kind of similar to the CERN in Europe, but I think it's still lower than the CERN. But nevertheless, we were able to test some samples. So those are a picture how it looks like inside. So the rays are actually coming from here. I don't know if you can see my cursors, and then going all the way through here to reach the samples. So the samples are placed on a mat like this, and then being irradiated. So we did two types of radiation. We did what's called GCR-SIM. So GCR goes for galactic cosmic radiation. And in that case, the samples were irradiated with protons, silica, helium, oxygen, iron, and proton again. And the radiation time was around 30 minutes with a dose of 0.5 gray. So those were established by physicians, be the approximate dose that you would get for a round trip to Mars. And we also irradiated our sample with SPE, which is solar particle event simulation. So again, SPE, it's only protons, but they just irradiated the samples with different energies of protons. And the total of radiation was 1 gray, and it lasted for approximately 60 minutes. So once we irradiated the sample, then we get them back to Tufts and analyze them. So what we did first was look at the FTIR. So we wanted to look at the composition in this range, which is the amino range of the silk, and see, well, do we have any change? And what we've seen, the only change that we could really observe was only for the silk column. So we irradiated silk silica, and silk Trolox. So again, Trolox is here to act as an antioxidant. And really the only change that we could notice was for SPE. So when we irradiated the silk sample by themselves with SPE at 1 gray. And here you can see a shift to the more crystalline region, 1630 for the wave number. Other than that, all the other samples look pretty much the same. And we did, on top of doing the SPE and the GCR at the NASA lab, we also did some gamma radiation, X-ray radiation, and proton radiation. Even though the proton radiation, you can see it's a lot higher in terms of units compared to the SPE, the LET, so the energy at which it's going to pass through the silk, is much lower. So really the most important data to look at in all of those are really for GCR and SPE, which are the most similar to what you're actually going to have in space. So this actually gave us a good data, like showing us, yes, the silk, no matter what, no matter the radiation, it's pretty stable, unless a slight change in beta sheet for the SPE. So here we just look at the silk contents, again, for the silk films, the silk silica, and the silk Trolox. And the most important here is to look at the beta sheets. And in all the samples, we can actually notice increase in beta sheets for the SPE mostly. They're all increasing, but the most important increase can be seen for the SPE, which correlates with what I've just shown you before. So now that we have all those samples and just the silk, we are also irradiating the samples with medication inside. So like I mentioned, we're going to include ampicillin and clavulanate and C. And so we are going to put drug inside the silk films, and the drug well, if I have the drug in the silk, can I recover the drug out? And also, is the drug more stable than the drug by itself? So this is something that is ongoing now that we are doing. So this was the part I mentioned before for silk stabilization, and now I'm going to switch more to drug delivery, which is a major component of what I'm doing over there. And I just wanted, again, to show you and remind you like all the different scaffolds that we can do. And I'm going to talk about most of them, I believe. So the first scaffold that I wanted to talk about are silk rods. So those were used for the sustained delivery of breast cancer therapeutic. In that case, we used anastrozole. So it's, again, used for breast cancer. And so the way they've done it is like they've done a silk fiber. So they just rotate it and did silk fibers until you obtain this rod that you can see on the picture over here. And the drug was loaded when the rods were stolen, and then they were just clipped at the end. And what they've shown here is this is just the in vivo that I showed here, but they used rats, and they injected the rats with high dose of the drug, a low dose of the drug. A, B, C, D are different rods. So A has the highest amount of drugs, B has the lowest amount of drug, and C and D are between A and B. And what we see is that both the high dose and the low dose, after like 2 days, they're out. So they go really high. So this is the plasma concentration of the rats. So it's really high at the beginning, but by, I would say, like not even 5 days, it's out of the system and it's out of the plasma. So that would mean you have no drugs. So you inject your drugs, you go above the therapeutic windows, and then you only have a limited time in the therapeutic window, and then it's out. And this is why you need to keep doing chemotherapy and go. And so you have all the side effects. Which makes it really tough. But if you look at the silk rods, you can actually see that beside the construct D, which after 28 days already decreased, if you look at A, C, and D, they're actually pretty stable, and they're able to maintain a constant concentration in the plasma up to 90 days. You start seeing a decrease after 68 days, but overall, you're able to really keep the concentration constant compared to 2 days, all the way up to 90 days. So this is one of the great things. So this is all the main component of why people want to use drug delivery system. And silk is actually, as I'm showing, really great for that. Another system, so we've talked about rods, and here what they've done is they wanted to compare hydrogel and lyogels. So lyogels are just like lyophilized hydrogels, like foamy, as you can see on the pictures. And what they wanted to see is, by changing the parameter, can we change the release? So in that case, what they worked on is they worked on the silk concentration. So what concentration they used to make those hydrogen and lyogel. And what they've seen is by increasing the concentration of the hydrogel, they were actually able to decrease the release rate. You still, with the hydrogel, you still kind of reach a plateau after 10 days, but you are able to decrease the release. And as for the lyogels, they had a much better control and much better sustained release. And if you look, so the lowest concentration was pretty similar to the hydrogel one, same for the 4%, but as soon as you go above 5%, you're really able to have a much better control over the release. And if you look at the highest concentration of the lyogel, which is almost 7%, you haven't reached a plateau yet after 80 days. So again, this is a great way to control your drug. And well, you might want your release in 10 days, so you can go to lower concentration, or you might want to obtain a release in 90 days. Well, then we know that by increasing the concentration of the cell, we can actually obtain this. And here what they're showing is, again, the swelling. So they are showing that the lowest concentration, the higher the swelling. And you think about it, if you have the lowest concentration, it means you're going to have a lot of water in your system. So once you're going to lyophilize this water, you're going to be left with a lot of empty space. So bigger pores, so you're going to have more space for the water to get in, and actually more surface contact as well with the drug. So it all makes sense that if you have a higher concentration, you're going to have smaller pore and less space for the water to come in. and swell the lyogels. And this is exactly what it shows here. So if you have, so the 3.1% lyogel, we have a much higher swelling ratio compared to the 6.7% lyogels. And they also shown that the cumulative release, so they took the gel and they either leave it native or they just compress them with 1,000 psi or 2,500 psi, and this using the lowest lyogel. And what they've seen is that if they compress, the more they compress it, again, the lower the release. And it makes sense because if you compress it, then you have less space for the water to enter, and you're going to have less surface contact between the drug and the water. And so the drug is not going to be able to get out that easily. So this is an example of how we use silk hydrogel for the sustained release of doxorubicin. So doxorubicin is a chemotherapeutic agent widely used. And the great attributes of hydrogel is that they're injectable. So you can put them in a syringe and just inject them to the site that you want. They are facile fabrication, especially with silk where everything is done in water. They have a high swelling ratio. They're also soft consistency. So they can also take the shape of whatever cavities where you want to put them. They have similar properties as the extracellular matrix. So all of those properties make them really great for drug delivery, tissue engineering, and cell scaffold. And so in the previous example, we show how different concentration of silk will affect the release. And here, on top of looking at the concentration of silk, they also wanted to check the boiling time. And I don't know if you remember, but at the beginning I mentioned that the more you boil the silk at the beginning, the lower molecular weight you're going to obtain. And what I've noticed here is that for the release of doxorubicin, we actually see a trend that the higher concentration will be the slower release, which again is in accordance with what they discussed before, but they haven't seen any change in the molecular weight. So if you boil yourself for 20 minutes or 45 minutes, it doesn't affect your molecular weight, only the concentration in that case. And so they were able to load different amount of the doxorubicin inside the hydrogel with different concentration, and you can see the picture below. So again, this example shows that by playing with the formulation and how, whether it's your construct or whether it's a concentration or the boiling time, how you can obtain your desired kinetic profile. Another example of hydrogel, this time is for the delivery of anti-VEGF therapeutics. So this is for the age-related macular degeneration. So this is like a loss of central vision, and it's leading to blindness and also visual impairments. And so we wanted to see by using the silk hydrogel whether we can have a more sustained release, because you don't want to go and being injected something in your cornea every other week, or it's just like for patient compliance, it's just not great. Like you want something better, that you get the drug there and then you don't need to go every week. And so this is what they've shown here. So they use silk hydrogel both with a high dose and standard dose, and they compare it with the standard dose. And the drug that is used in that case is bevacizumab. I'm not sure about the pronunciation, but it's written. And so what they've seen here in vitro is that you reach your higher concentration after 6 days. So this is where you reach your point, and then you start slowly decreasing. And the drug by itself goes below the quantitative limit after 30 days. But if you use both the high dose gel and the standard dose gel, you're still releasing the drug after 90 days. So again, we are by 3 times the release profile. And even though we're still decreasing, then it's kind of staying constant between day 30 to day 90, I would say. So based on those in vitro results, we actually then went to in vivo. So in that case, we used Dutch belted rabbits. And so they injected it with the same system. So they did a high dose gel, a standard dose gel, and the standard dose control. And we noticed the same thing in the rabbits. So the concentration of the standard dose control, it was below the limit after 30 days. But both the high dose gel and the standard dose gel, even though they just reach the below quantitative limit after 90 days. So we saw the same pattern that we actually seen in vitro. Now we're going to switch to a different type of construct. So we talked about hydrogel mostly, and now we're going to talk about silk microneedle patch. So microneedle patch is, I feel like it's being more trendy right now, and it's more and more people are doing study on those, and they're great for transdermal delivery. So think about vaccine, drugs like painkiller, and they're painless. So compared to like an injection, you won't feel them because they're going to sit right above the nerve. So they're non-invasive. And also by taking those, you can avoid the systemic circulation as well as the gastrointestinal degradation. So if you think about painkiller and you have to take the drug, ibuprofen, it goes into GI, you can have degradation, you can have side effects. But if you put it on your skin and it's delivered by the dermatome or the nerve system, then you avoid all of this. This is the process to make actually the microneedle patch. So we have a PDMS mold, and we're going to cast our silk drug solution on it, so the same liquid silk solution that we have. We're going to apply some vacuum to remove any bubbles and make sure we push all the silk with the drug inside the needle. We then apply a cell backing. And to make sure those patches don't dissolve readily, we have to water anneal them to induce crystallization. And here on the right, you can see some STM pictures of our microneedle. So one really great project that we're working on is using those microneedle for contraceptive delivery. So this is a project that is funded by the Bill Gates Foundation. And they actually want to develop the usage of contraceptive in the developing country. So if you think about country where they don't have really access to doctors or it's a stigma to use it, they want us to make a patch that you can just take at home and apply by yourself. So this will be all done in privacy. It will also be pain-free. And also using the microneedle, we can stabilize the contraceptive for a month or a year, even at elevated temperature and humidity. And so what we've done in that project is we check both the release by using different concentration of silk, but also different molecular weights, so different boiling time. So what you can see on the panel A here is we use 10% and 7% concentration of silk, and we also use low molecular weight, high molecular weight, and medium molecular weight. And what we've seen here is that, again, the higher concentration of silk really give us a slower release of the levonorgestrel. So yeah, in that case, the drug that we're using as a birth control is levonorgestrel. So it's already readily used. This is also what they have in the USA as the Plan B, what is called as the Plan B. And also, we didn't, I mean, the notice in the molecular weight wasn't that clear. So you can see the medium molecular weight is higher, whereas the lower and the highest were kind of in the middle. So the molecular weight trend wasn't really clear, but for sure we could see again that the higher concentration of silk will give us a slower release. We then also wanted to add either a surfactant or solubility enhancers, so twin or beta-cyclodextrin, to see whether that would help actually to release the drug faster. And this was efficient. So as you can see, for example, at 40 days, we are at 50%. Whereas at 40 days with the other one, we're just above 40%. And we're able to be above, we're actually able to reach above 60% release after 60 days that we cannot reach without the twin or the beta-cyclodextrin. And the goal for this study is to go above 6 months. So we are trying, working on different formulation right now to make sure that we can reach this. And another, we haven't done any in vivo, but we actually contacted any CRO and we should start this soon. So it's not something we can do at Tufts, because for the in vivo for microneedle, you want to use mini pig. You don't want to use rats. So it's something that CRO will be doing. So we will give them the formulation and we will see the PK, the pharmacokinetic study, as well as the dermal tolerance. And this is something that should be done in the next couple of months. Another construct that we have been using, and we kind of talked about it at the lyogel, but those are like silk foam. So silk foam compared to lyogel, they will be more porous. Especially, and it depends again the way we're using it, but in that case, they're like done by cryogelation. And so they will have those sponge-like porous microstructures, which will make them highly porous. And those big pore will again yield to like a high swelling ratio. We're also adding an additive, which is glycerol, which give them like a rapid compressive recovery. So if you take this foam and you put it in water and you compress them in your finger, and then you remove your finger, the foam is just going to gain back its shape. So this would be great for implants. But in general, cryogel are widely used in tissue engineering, drug delivery, cell scaffold, bioreactors, and also chemical separation. So what we wanted to do here is use ciprofloxacin, which is a widely used antibiotic. And we wanted to see how by changing the formulation of the drug, we can change the kinetic release. So if you use ciprofloxacin by itself, you have the molecule down here. It's not water soluble. So it would have to be loaded either with organic solvent that we're trying to avoid, because this is the whole point of using silk, is that we don't need any synthetic solvents. Or we can use also ciprofloxacin HCl, which by itself is soluble in water. And so we loaded 3 different drugs. So we loaded the powder, like the non-soluble water. We loaded the soluble water, and we as well as loaded the solution. And what we've seen is the solution is out in not even a day, while the soluble powder takes much longer, has a more controlled release, but still reach a plateau by 100 days. But if you use a non-soluble powder, you're actually able to obtain a really sustained and controlled release that goes for more than 200 days. So this was, again, another parameter to control your release that we could use with silk. But something great is if you think about it and you use an implant, and we talked about like silk can take from month to year to degrade. And if you want an implant or if you want tissue regeneration, you don't want the silk to be there for too long. You would like the silk to just disintegrate so the tissue can just grow again and just fill this cavity that they were in. So what we did is we added here a protease 14. So it's an enzyme that is actually eating up the silk fibrin. So we added this protein to our foam by 0.1 and 0.01%. If we added more than 0.1%, we just couldn't form any foam. And we compared the degradation with just the foam in a regular, either a solution of protease or in PBS. And so the foam in the protease solution will degrade really fast. The foam in PBS will not degrade. We will only lose approximately 25%. And those 25% are the amount of glycerol that we're actually adding to make them more plasticky. And so this is not even the silk, this is just the glycerol leaching out of the silk, this 25% loss. The 0.01% was pretty similar, at least until 25 hours, it was really similar to the foam in PBS, while the 0.1%, the green one, decreased by almost 50%. And if you see over 30 days, the 0.1% almost reached 60%, while the 0.1% reached 80% degradation. So again, like this is another parameter. By adding protease, we're actually able to make our foam degrade faster. And what we've seen showing here is, again, using our same formats of CIP-HCl powder, solution, and the non-soluble powder, whether the protease will affect the speed of release. And it didn't, like the protease didn't affect the release, it just affected like the shape of the foam. So if you look at here, this is after 30 days, so the no protease, the foam is intact. And the 0.1% really decreased by more than half, or the 0.01% decreased, like I would say, by maybe 25%. And the only difference here that you can see with the 0.1% protease where it stopped releasing, it's actually since the foam is degrading, the drug is just coming out. And when we change the media, we just have to remove the drug. This is, again, I think this is the final one. So this is a silk film, so again, a different format that we use for the sustained release, again, of doxorubicin, so similar to the hydrogen that I showed at the beginning. So what you can see on the picture is just silk films with different amount of doxorubicin. And doxorubicin is a red drug, so the more you're going to add of the drugs, the redder the films will be. And they're great because, I mean, depending on the application, a foam might be better, or hydrogel might be better, or a small film might be better. So it really all depends about your application, but they're all really great constructs and useful constructs. And so they made those films by 2 ways. So first, they just use a silk solution directly mixed with the doxorubicin. They just casted this solution onto like a PDMS mold and let it dry in the air. And without touching them, if you don't do the water annealing of those films, they're just going to be soluble. If you put them in water, within 60 seconds, they're gone. They just dissolve. But they also took the same thing, but did some H2O annealing, so at different temperature. And those which we refer to stabilized 6 films. So those films are non-water soluble because we induce the beta sheet formation by doing the vapor annealing. And again, all of this is done in water. You don't need to use any solvent or any harsh condition, which is great, especially if you have lay-by therapeutics. So what they've shown here is this is the cell viability. So those are human breast cancer cells, so MDA and B231. And we loaded the drugs, the gels with, the films with 40 microgram of doxorubicin. And you have a control. You have your soluble silk films, which are the one that no water vapor annealed. You have the diffusible doxorubicin, which is just your free doxorubicin. And then you will have your soluble silk film plus doxorubicin and the stabilized silk film plus doxorubicin. And if you look at the control and the soluble silk film, they don't have any, the cells are just growing normally. They don't have any drug in them. But if you look, you have a pretty similar pattern for both the soluble silk films and the diffusible doxorubicin. But so they are toxic in 8 weeks, and then the drug is out and they just start to grow again. But if you use the stabilized silk films, which is not dissolvable, it's just going to keep a sustained release of the drug. So even your viability is really low even after 12 weeks. So this is another parameter. So on top of the molecular weight, the drug format, the boiling time, now we're actually looking at how is the crystallization of the silk affecting the release. And this is the in vivo data with the mouse, I believe. So again, what you see here is that after 6 weeks, if you look at the compound which has the stabilized silk film, this is the only one with the lower tumor. If you look at the stabilized silk film without doxorubicin and the control, they are pretty much the same size. If you look at doxorubicin, you have a decreased size of the tumor in bioluminescence, but it's still higher, and it's pretty similar to the soluble silk films because the drug is just coming out right away. But the best result were obtained with actually the stabilized 6 film with the dogs. And again, this is all due to like a sustained release of doxorubicin over weeks, months, which allow the tumor to remain small. You will see the same. So if you look at the tumor weight after 6 weeks, the tumor weight is pretty similar between the control and the stabilized silk film. So both of them non-containing any doxorubicin in it. And then the soluble silk film again and the doxorubicin by itself are the same in size, but the lowest tumor weight was actually again for the stabilized 6 film containing the doxorubicin. And all of those, whether it's the control, doxorubicin, stabilized, non-stabilized, they all have a metastasis in the bone. We have same metastasis in the liver and the lung for the control and the stabilized 6 film, which was a control, but you also have lower metastasis in the brain using just the stabilized cell film. And if you look at the free doxorubicin, it's actually a much lower metastasis in the liver, but you still have metastasis in the lung, but no more metastasis in the brain. But if you look at your stabilized cell film, so in that range, you actually have no more metastasis in the liver and small metastasis in the lung. So again, this shows that our compound with the stabilized cell film in the docs, it's much better in handling the tumor than even the doxorubicin by itself. This is looking more at the toxicity and the systemic impact. So what they wanted to check the heart rate after 6 weeks. And again, the heart rate for the control and the stabilized silk film were similar. And if you look at the lower heart rate was actually for the doxorubicin IV, then followed by the soluble silk film, so the doxorubicin in the silk film. But if you look at the stabilized silk film with the doxorubicin, the heart rate was similar to the control and the stabilized silk film. And if you look at the histology over here, you also see no acute inflammation. And we know that silk actually doesn't induce any immune response. So by showing you all those examples, all those different constructs of silk, I hope like you get a sense of how silk can be used for drug delivery. And this is all due to that you can use, all of this can be done in aqueous processing, ambient processing. We have all really highly tunable system, whether it's mechanic, degradation rate, form. And this can be used for the stabilization, but also you can tune your release, whether you want to release in a day, you want to release in a year, you want to release in 3 months. And all of this can be achieved by silk protein. And I've shown you like today, everything was done with drug delivery and drug stabilization, but our group is also working a lot with tissue engineering, 3D printing, 3D models for brain disease. This has been really widely used as well, but a lot of other people in my groups are working on this. So we have a really high group of approximately 60 people. So we all do a lot of different cool stuff. So I would like to thank my team in the Kaplan Lab. So again, those are just some of my collaborators, my PI, David Kaplan, which is a really great PI, and some of the other postdoc and technician. But again, it's like, we're like around 60 people, so I wouldn't be able to write everyone. I would like to thank our collaborators, so the people from NASA, Stanford, MIT, and also some industry collaborators. And finally, the grants funding from NASA and 3H, the Bill and Melinda Gates Foundation, NIH, NSF. And thank you to everyone for listening to me. I know this is the end of the day for you. And if you have any question, and we're always open for collaboration, we love collaboration. So if you feel like there would be something that could meet, we'd be happy to discuss by email. Thank you so much.
So thank you, Laura, for the very interesting presentation. And you just showed us how many ways we can use silk. I really love the way to use silk in the space. Do you have any a drug or compound in the space right now?
So we don't have anything in space. We don't have any mission going on. The only thing that we've done is we just took 2 drugs, so ampicillin and clavulanate, and we irradiated them at the NASA lab. So now we're actually analyzing all the data to see whether is silk helping with those. I mean, ideally, we would love to be sending those samples to space. Next mission, or depending on the funding, how it works. That would be really cool. We just want to see now with the simulation of radiation on Earth that we were able to do at the NASA lab, is it actually working? Do we actually recover more drug? And if that works, then maybe NASA will ask us to send some sample for analysis.
Oh, very nice. We also have a couple of questions. The first one is from Rafael Freitas. Rafael, if you'd like to do it yourself.
Hello, hi, thanks for the talk. As just like a curiosity, I was wondering whether there is any limitation in the size of molecule that you can sort of couple with the silk. For example, if I can, for example, put like a big protein or a DNA, do you have any idea on that?
So that's the great thing, is that you can pretty much put everything. So we've worked with antibodies, we've worked with RNAs, we've worked with small drug molecule like doxorubicin. I haven't done much work myself on proteins or antibodies because I'm more of a chemist, so it's just a lot easier for me. But I know a lot of papers have been published from our group for RNA stabilization, antibody stabilization, and things like this. So we have no limitation in terms of size. Whatever you want to put, we also work with vaccine. So we put, the only issue is sometimes the interaction between like a big proteins and the silk. So sometimes you can have a lot of interaction that you have an issue releasing the protein. But then if you add some surfactants or solubility enhancer, it's something you can work on. So yeah, I could say there's no limitation in the size to put in the silk samples.
Okay, thanks.
Sure.
Thank you. We have another question, I think, in the same idea. It's from Martin Cavalcanti, and he asks, is there a specific group of drugs that can be tested with the silk system, or is the group not compatible?
No, again, I mean, it's pretty much everything is compatible. The only issue would be the interaction between the silk and the protein. So you could have pi-pi interactions or hydrophobic interaction, things like this. But no, this is great. Everything is working. We're able to deliver whatever we want.
We also have a question from Igor Ahuda, and he asks, how do you see the insertion of this type of technology in public health system? Do you have anything at public health right now?
Well, I don't know if that counts, but for example, I think the birth control microneedle, it's something contributing to the public health system. Maybe not in the US where it's readily available, but if you think in country more like Africa or country where they don't have access to birth control, this is a great way to help the woman just prevent unwanted pregnancy. This also could help for the cold, again, to avoid the cold, how you call that, like all the cold storage. So you will do like, and if you go to country, same where they don't really have access to all those cold storage, well, they could store vaccine for much longer and things like this. Yeah, but as of right now on the market in the public health, no, I don't think we have anything as far as I know. We're working on it.
Interesting. Another idea that I had, have you tried this silk microneedle patch in infectious disease, like bacteria in the skin or maybe some parasites?
Not that I know of. We haven't. We are actually, so the company we're working with for this microneedle birth control delivery is actually working on vaccine delivery. So this is something, and I think they've shown, so they work on the flu vaccine, and I'm sure they're going to be working with COVID vaccine later on. So they are the ones, so it's already on the market. I believe it's a spin-off from our lab, or I'm not sure, but David is on the advisory board of this company. So working closely with them, and yeah, so they are working for vaccine.
Another question, what's the cost of this micro patch or the biofilms?
I mean, it's like if you have the molds, the silk costs nothing, right? I mean, the price is just, it's not like a fancy synthetic polymer. It's really available. It's dirt cheap. And if you, I would say what is the most expensive, it would be the microneedle mold, right? Once you have your mold, then you just use your silk and it doesn't cost you much. And the mold, for example, I can give you an idea. It's the mold we order for this microneedle were $1,000. And you can just reuse it over and over and over and over again. So the cost is really limited in that case.
Good to know, because here we have a problem with cost, so it's nice to have something that's cheap.
Yeah, and it's really hard to find. We had a lot of issue finding actually a company. You would think this would be readily available, and actually I couldn't find anyone in the US. So I had to order those molds from Ireland. And I had to get them shipped from there because just no one in the US making the mold that we wanted. So I think that was like the biggest difficulty. But once you have the mold done, then you just put whatever solution you have and you're good to go. So it's really not an expensive process.
I'm probably going to send you an email so we could test maybe this patching leishmania or other bacteria.
Yeah, for sure. I mean, like I say, we love collaborating. David loves collaborating, and we have the system so we can help with anything you need.
Okay, and then we have another question from Michelle.
Okay, thank you. So, Laura, congratulations. Very innovative work. Excellent contribution. Congratulations. Really nice.
Thank you.
I love to hear that the system induces a decrease in brain metastases and also a decrease in metastases overall. So promising for sure, hopefully. Excited to see in human clinical studies, and please come back to tell us how it will be in the future. So just out of curiosity as well, thinking about addiction, there is a problem all over the world, especially in US actually, and the treatment of it. So there is not a yet treatment for addiction. And I was thinking about the system and how it has this controlled drug released. So could be incorporated in that way, I mean, in that avenue for treat addiction in this way. I'm not sure if it's more or less the kind of treatment that we have nowadays for addiction. It's a long-term release drug treatment, and I'm not, as you said before, you can put everything on that and that might work. So I guess it's gonna be a nice overview for you too and your group try to think in that direction, because we must find a solution soon for that problem all over
This
the
is this is really great. This is a really great point, and I totally agree. We haven't gone in that direction, like not for drug addiction. The only thing we're looking at, which is kind of related, is for the painkiller management, and we actually have, I don't know whether I'm kind of allowed to talk about this, but we have an industry collaboration to deliver painkiller. Because, you know, especially in US, like the opioids. So a lot of people before for pain were treated with opioids, like tramadols and things like this, and those are really highly addictive. And so now what we're trying to do is using our microneedle patch, how we can deliver pain, but not using opioids. So there's all the drugs. One of them is ketorolac, for example, which is kind of an NSAID, but really high and similar to morphine. So they usually give that now to avoid the opioids. And so we're checking how we can release this again with a microneedle. I know there is a couple of drugs that they give to people for addiction. Like you said, people have to go to the centers to get them administered, I believe. I'm not sure how that works, but I've heard a bit about it in Boston because we have a lot of issue with that. And so you have the centers that people have to go every morning to get their, I don't remember the name of the drug that they're giving to people. But anyway, it would be great indeed if you can just give a patch to the people or inject them with a gels or a foam. I believe a patch would be kind of, I don't know how that would work because they could just transfer from people to people or things like this. But let's say you inject foam or hydrogel that could just release the drug over time. Yeah, this would be great, actually. I really like the idea.
Thank you for your answer. But actually, something came to my mind right now. If you pass from person to person, could it be a contamination in the system, or you think that'd be contaminated free patch?
I don't know. I mean, I really don't know about this because even if you use the transdermal, you're still passing through the skin layer. So I don't really know the biology, so I don't know. But I would assume, like, yeah, it's not a needle, but I would assume if you're passing from people to people. Yeah, I would assume that you could have some contamination, but I'm not sure about this.
Okay, thank you very much, Laura.
Thank you.
So Laura, thank you very much again for accepting our invitation. It was a pleasure to hear you about your work. And please send hi to David for me.
I will. Thank you for having me. It was really great.
Now Moacir will take over to do our closing remarks. Thank you.
Thanks.
Thank you, Lara, for your lecture. It was amazing. Thank you so much.
Thank you.
Gente, então, eu queria agora, né, para terminar, eu queria que César, Michele Melgarejo, Dani e Michele Cristina abrissem os videozinhos deles, e principalmente eu queria que Juan abrisse o videozinho dele. Cadê Juan? Que Juan tirou as fotos de todo mundo, mas até agora está escondido. Não apareceu ainda.
We are opening our camera so we can take a picture to put in the website.
Cadê Juan? Alguém tá vendo ele? Eu não tô vendo ele. Olha ali.
Olha ali.
Apareceu.
Agora. Então, let's take a picture. Everyone's smiling. That's it. So, Laura, thank you. Now I have to move and start to talk in Portuguese because I will talk to the audience because some notes that I have to do with it. Okay? Thank you so much.
Bye.
Bye. Juan, não desligue sua câmera não, fique ligado que eu vou fazer um agradecimento especial para você. Olha então, minha gente, esse menininho aí que está aparecendo com a legenda de Internacional Symposium é Juan. Se não fosse Juan, provavelmente a gente não estaria aqui. Eu atazanei o juízo desse menino, acho que desde o começo que a gente pensou em fazer o evento, e o coitado provavelmente deve estar sem dormir há uma semana, porque o bicho foi usado. Mas, enfim, né, Juan? Eu queria agradecer especialmente a você, que foi a mão de obra que estava à frente de todos os pedidos de todos os professores. Então, muito obrigado pela sua dedicação e pelo carinho que você levou à frente o congresso. Muito obrigado mesmo. Então, se você quiser dar um oi pro pessoal, viu, para eles escutarem sua voz.
Oi, gente. Eu que agradeço a todos os professores aqui, especialmente a você, Moacir.
Foi um prazer participar desse congresso, muito bom participar da comissão organizadora. E eu agradeço a todos que compareceram ao congresso. Espero que tenham aproveitado alguma coisa, que tenham tirado do congresso alguma coisa. É isso, só tenho a agradecer.
Obrigado, pô. Então, antes de falar algumas coisas para vocês relacionadas ao certificado e de contato com os palestrantes, eu vou passar a palavra para Dani, César, Carol, Michele para falar. Eu vou passar primeiro para a Carol, que ficou com o árduo trabalho de convidar os palestrantes aqui para a gente. Carol, fica à vontade.
Então, gente, só agradecer o convite, né, a ideia de Moacir aí, que entrou em contato comigo. Foi um prazer imenso. Espero que a gente reproduza, né, essa ideia nos próximos anos, porque a gente aprende bastante. Sai um pouco da nossa zona de conforto, das áreas que a gente sempre interage, né? Então, acabei aprendendo várias coisas hoje nessas palestras. E foi um prazer imenso. Espero que vocês tenham aproveitado também. E contem comigo para as próximas, né?
Obrigado, Carol. César, Dani.
Então, primeiramente, parabéns, Moa, pela brilhante ideia. Então, realmente, o simpósio, ele veio trazer as informações, né, que os nossos alunos queriam, e foi uma oportunidade de mostrar a eles como é importante, né, esse processo de troca, né, de informação. Nós, aqui do Brasil, com os diversos pesquisadores, então, vocês aí, especificamente, a Carol, a Michele Melgarejo, a Michele Pereira, né, trouxeram aí brilhantes pesquisadores, né, e as possibilidades diversas de pesquisa. Então, foge um pouco muito da área de muitos que estão aqui, né, mas isso não quer dizer que a gente não possa interagir. Então, abre aí um leque de possibilidades, e isso é muito importante. E outra coisa que é bom destacar, que o nosso programa, ele aprovou um print, né, e a gente está aí com o processo de captação de estudantes para a ida, né, para algumas instituições. Não quer dizer que estudante que não consiga entrar no projeto específico de esclerose, ele não possa ir para o print, então a ProPG, ela tem edital aberto para o estudante que queira se candidatar ao edital dentro da inovação em saúde, ok? Sendo da área inovação em saúde, ele pode sim se candidatar. Não só esse edital específico print, mas fiquem também atentos aos outros editais, que são muito importantes, a essa necessidade de internacionalização mesmo, tá bom? Grande abraço a todos, foi ótimo, foi um prazer.
Obrigado, Dani. Mi Pereira. Melgarejo, tá prontinho aí?
Não, só agradecer a participação, agradecer que vocês trouxeram esses palestrantes, que a gente aprendeu tanto, coisa boa trocar informação, coisa boa falar inglês um pouquinho. Estou saindo daqui cheia de pensamentos de parcerias, espero que eles se concretizem. Parabéns, Moa, pela ideia, e vamos repetir com certeza, podem contar comigo aí.
Perfeito.
Bom, foi excelente. Adorei muito, acho que aprendi muito, né, durante esse evento. Parabenizo, né, a toda a comissão pelo empenho, Moacir, que mesmo de longe, né, articulou com todos os professores, né, de todos os lugares aí. Foi muito produtivo e com certeza teremos aí parcerias bem interessantes para os alunos, para os professores. Parabéns, pessoal. Espero que todos tenham curtido.
César?
Cara, eu só posso dizer uma coisa. Foi massa. Entendeu? A gente ralou um bocado. Foi muito bom ter trabalhado aqui com vocês. Eu estou o tempo todo olhando para o lado, que eu estou transmitindo aqui pelo YouTube. Eu acho que vai render muitos frutos ainda em relação a esse evento. Eu acho que todos falaram aí em relação ao crescimento do programa, principalmente o crescimento da Universidade Federal e do Estado, vai ser muito, muito interessante e acho que muito frutífero, principalmente pela fala de cada um. Eu até brinquei, Moa, que quando apareceu a foto do secretário lá, que o Daniel falou, eu mandei para ele. Ele ficou super feliz com essa possibilidade da parceria, já avisou que na próxima semana ele já está indo no consulado americano para ver parcerias do consulado para, junto com a FACEP, trabalhar alguns editais específicos. Eu espero, obviamente, que o PPGIT possa entrar nos possíveis certames que venham aí e obviamente, ser competitivo para alcançar êxito. Fico feliz também pela harmonia que a gente teve aqui na gestão, na elaboração e principalmente na participação de todos aqui nesse evento, e torcendo aqui para que no próximo ano a parte da equipe aqui tenha a possibilidade de fato de visitar a Europa, né? Estou prometendo a visita lá a Moacir. Antes dele voltar, eu vou fazer uma visita e visitar também o Adam na República Tcheca, não é? Já vou pedir autorização a Daniela aqui em público para me liberar para fazer uma visita, é a trabalho, de qualquer forma. E no mais é isso, pessoal. Fiquem de olho sempre no PPGIT, tá? É um programa de excelência na área de saúde. Acessem o site do PPGIT, o canal do YouTube, para estar recebendo informações, o Instagram e o Facebook. Sempre tem notícias legais e também o programa também tem linhas de pesquisa que são muito alinhadas com tudo que foi apresentado aí, que vocês viram hoje. No mais é isso. Um grande beijo, um grande abraço a todos aí.
Valeu, César, obrigado. E no começo, quando a gente pensou no evento, a gente pensou ele só para pós-graduação, mas a procura pela graduação foi muito grande, e aí os alunos de graduação que estão assistindo, né, o evento, essa cara que vocês estão vendo agora é a cara do PPGIT, né, eu, Dani, Carol, Micheles, César. Então, se você é aluno da graduação e está procurando um programa de pós-graduação para fazer, você já achou. Então, estamos aqui, e do mesmo jeito que o pessoal do exterior, que foi todo mundo super aberto a colaborações, nós aqui, professores do PPG, também estamos abertos a colaborações, a vocês tirarem dúvida, entrem em contato com a gente. Adam e o Richard tiveram uma palestra com a gente de manhã e no começo da tarde, ambos já mandaram um e-mail agradecendo e disseram que adoraram participar do evento, e todos cobrando, claro, que o próximo evento fosse em Recife, presencialmente, se tudo der certo, assim esperamos. E lembrem muito que a gente colocou lá, é o primeiro simpósio, né? A ideia é que a gente consiga fazer ele sempre visando essa internacionalização, principalmente dos nossos alunos vinculados ao PPG. Todos os professores que vocês viram hoje nessas apresentações estão relacionados a outros professores que trabalham no PPGIT e que estão de portas abertas para vocês. Então, pensem nisso, né? Vão agora para dormir ou fazer, sei lá, quer dizer, dormir para mim, para vocês vão aproveitar a noite e etc. E eu queria só agradecer mais uma vez. Então, qualquer dúvida, vocês entrem lá no perfil da gente do YouTube, tudo está gravado lá, quem quiser assistir mais ou checar algum detalhe que passou despercebido, vai lá que está tudo gravado. Se quiser tirar alguma dúvida com a gente, pode entrar no site do PPGIT, que tem um e-mail de todos os professores que estão aqui falando com você pode falar cada um individualmente, vocês podem, durante as apresentações, vocês viram que a professora Maria Daniela e o professor César têm experiência com nanotecnologia, né, e ciência de materiais. A professora Maria Carolina Cioli, jogando uma leishmania ali no meio do PET, né, também puxando para a sardinha dela. Michele Rosa puxando para neuro. Michele Pereira para o câncer de pulmão. Eu para o câncer de pâncreas. Então, todo mundo aqui tem... E, claro, é uma ótima oportunidade para a gente também sair do nosso mundinho e aprender as diversas áreas, né? Mesmo não sendo na minha área de expertise, nas outras palestras eu aprendi muito e a gente consegue ver colaborações como com o Steve, por exemplo. Fiz uma pequenininha perguntinha ali para ele, eu vi que ele se animou e aí eu me animei também. Então, isso é um momento muito bom para a gente. Então, sobre os certificados, tá? Para vocês não começarem a encher Juan amanhã de e-mail, que Juan é quem manda os e-mails e tudo para vocês. Vocês não precisam amanhã mandar vários e-mails perguntando sobre o certificado do evento, tá? O evento está registrado pela Federal. A gente precisa mandar um relatório final do evento, que a gente tem até um mês para mandar esse relatório final do evento, depois que a gente checar a presença de todo mundo. E depois que a gente checar as presenças, a gente envia a lista para a Federal e ela vai começar a emitir os certificados. Quando os certificados estiverem prontos, aí a gente vai mandar novamente de volta para vocês. Ah, professor, vou precisar, porque eu vou fazer um concurso, eu vou fazer uma seleção. Aí você pode mandar um e-mail para aquele e-mail que você recebeu, a confirmação do e-mail, e a gente vai gerar uma declaração para você, tá? Não um certificado. uma declaração. O certificado quem vai emitir é a UFPE. Então, antes de 40 dias, provavelmente, tá? Vocês não precisam mandar e-mail perguntando sobre o certificado, que provavelmente ele ainda não vai estar pronto. Mas assim que o certificado estiver pronto e que a gente checar as presenças, todos vocês irão receber os certificados. Tá ok? Então é isso, gente. Vou declarar agora, né, encerrado o evento. Mais uma vez agradecendo a comissão e mais uma vez agradecendo a todo mundo que permitiu que a gente ficasse com mais de 120 inscritos, no mínimo, durante todo o evento, né, conseguindo chegar entre 150 e 180 inscritos. Então, muito obrigado a todos.
Ô, Moa, faltou a abertura das câmeras para dar o tchauzinho aqui, para tirar a foto final, né, o Juan?
Aí.
Dá o tchauzinho aqui do final do evento.
Quem puder abrir a câmera, ou é a Vanessa Brito. Vanessa Brito, MC, abra sua câmera, vá, apareça. Isaac é de César, bora, Isaac.
Eu não estou nem vendo, Isaac, aqui.
Nena, eu vou dizer a Nena que você não apareceu.
O pessoal não gostou, não, então deixa para lá. Vamos.
Só vai
No
ganhar.
final do dia já tá todo mundo descabelado.
Pois é.
Na foto. Não aparece.
Tá bom.
Gostado, obrigado, viu? Boa noite aí para vocês. Boa noite para todo mundo. Tchau, tchau.
Vai lá.